Okay, so we are going to continue now with the posteriori preference articulation. And these are very important methods. We're going to see only two, but these two are really very popular. At least the first is very popular, the linear combination of weights. And the second is actually a very interesting method because it has properties that allow its, what the hell is going on? Its generalization. You need to put a passport here. That's what I don't like about Windows. It's alive. Jesus Christ.
You want the net?
No. No, I don't need it. Yeah. Okay. Wow. Even Acrobat is failing. Okay. There we go. Okay. So in this case, as I mentioned before, in a posteriori methods, you do you have to assume in this case that we don't require prior preference information from the decision maker. And of course, metaheuristics fall within this category because when we perform the optimization, we are assuming there are no preferences from the user. And these two methods actually follow from the Kohn-Tucker conditions for optimality or for non-inferior solutions. And as I said before, they are very, very popular, at least the first. So Loftus-Sadek, as I mentioned before, in 1963, was the first to show that the third of the Kohn-Tucker conditions for non-inferior solutions implies that these solutions might be found by solving a very simple scalar optimization problem in which all we do is to produce a weighted sum of the components of the original vector valued function. So it looks like this. We have k objectives, so we simply add these objectives by multiplying each objective by a weight. These weights have to be greater or equal than 0. And there is an additional condition, they have to add to 1. And basically, we can generate parametrically, by parametrically varying the weights, we can generate a set of non-dominated or non-inferior solutions by using this very simple expression. This was proved since 1955 by Sativ for a problem having two objectives. So it's a very simple way of solving a multi-objective problem. Now, there are some remarks that are very important. These weighting coefficients do not really reflect the relative importance of the objectives. These are only factors that will allow us to produce different points in the Pareto front. Also, it's important to take into account that the units in which the functions are expressed are important in the actual optimization. And normally, most people tend to normalize the objectives. Because if you don't do a normalization of the objectives, then it could happen that you have one objective that is given in very large amounts and another objective that is given in very small amounts. For example, you are adding weights, and it's thousands of kilograms, with displacement in a structure, which is a very small amount, less than 1. And if you add these two amounts, then the result doesn't make much sense because the large amount is going to have more importance than the small amount. So you normally have to normalize to do this. And also it's very easy to prove, and this has been proved by several people, that if you use a linear combination of weights, like this expression, this one, then this is unable to generate non-convex portion of a Pareto front. And this is regardless of the weights that you use. And this, of course, is a serious limitation, which is the reason why many people don't like to use this method. This is a very simple example. We are using, for this Pareto front, we're using a linear combination of objectives, and you will see that the linear combination will only produce these points, A, B, and C, but is not able to produce any points here. So it's a serious limitation, which is the reason why linear combinations of objectives is not seen as a nice method for multi-objective optimization in evolutionary computation. This is the closest thing to the devil. If you say in your paper in the abstract, I'm using a linear combination of objectives, your paper will get rejected without even getting to the algorithm proposal. So it's an old method. It has been used a lot. It has some advantages, and we will get to that later on. It's not everything is bad about this method, but it has some serious limitations. Epsilon constraint method is more interesting. This method can also be derived from the Kohn-Tucker conditions. Yes? Normally you select the weights in a uniform manner, varying from 0 to 1 for each of the objectives, and you try all possible combinations. For example, you say I'm going to have 10 intervals, and you generate 10 values that are equidistant for each weight, and you try all the combinations. That's normally the way it's done. But there are methodologies. We will get to that later on. There are methodologies to do that. So the epsilon constraint can also be derived from the third Kohn-Tucker condition for optimality. I won't get into the details on how this works, but this is a very interesting method. Basically, what we do in this case is assuming that we can bound the Pareto front. We're going to minimize one objective while keeping the second objective as a constraint. But this is not the same as we saw before with lexicographic ordering. Let me show you graphically what we will do. I'm going to fix one objective, for example, in this case, around point C. So I will start my single objective optimization somewhere here. I will keep moving until I reach point C. And this epsilon in here, epsilon 1, is acting as one constraint, so I'm fixing the value for the second objective. Then I change this epsilon to another one, and I produce another point. So you can see here how in the previous example, in which using the linear combination didn't work, in here I can manage to produce a solution in the non-convex portion of the Pareto front. So this works regardless of the shape of the Pareto front. It doesn't matter if the Pareto front is disconnected. So it's very powerful, because this is the method that in the old days people used when they didn't know where was located the true Pareto front. Using this method, you can find at least a few points of the true Pareto front by doing several single objective optimizations. Now, why is that this method is not that popular? Well, it has two problems. The first problem is it's very expensive to use, because for each point, you have to run a single objective optimizer. And this may require hundreds, even thousands of evaluations just to generate a single point. The second disadvantage is you need the nadir point. For this method to work, you need to bound the Pareto front. For bounding the Pareto front, you need the nadir point. So this is also, in many cases, not possible to obtain. As I said, in general, this problem is not solved. For two objectives, it's possible. For more than two, is an unsolved problem. However, whenever it's possible to apply this method, some people have used it to get an idea of where the true Pareto front is, particularly in a real-world problem. It's not difficult to implement. It's just very costly because of the many single objective optimizations. So this is a highly recommended method when you want to estimate where is the true Pareto front in a real-world problem and you don't have much information about the problem, as long as you can afford it, because you will require a lot of time to do this. Okay. So we pass to the third group, the progressive preference articulation. These methods operate in three stages. First, we find a non-dominant solution. We show the solution to the decision maker. We get the reaction of the decision maker. He says, I'm happy or I'm unhappy with the solution. And he modifies his preferences on these objectives. and we repeat the step. We try to find another solution now, given the new preferences of the user, and we stop when either the decision maker is satisfied or no improvement is possible. The decision maker is changing his preferences, but we cannot get anything better of what we already found. So in that moment, we can stop. So we will see quickly 3 methods within this family: the probabilistic trade-off development method, the STED method, and the sequential multi-objective problem-solving method. So in the first is called ProTrade for short, and it was designed to handle risk when developing trade-offs for the objectives. And at the same time, they wanted to incorporate preferences from the decision maker in a progressive manner. So the idea here is that our multi-objective optimization problem has a probabilistic objective function and also has probabilistic constraints. That means we will define a certain probability function that will tell us how likely is some constraint to occur or not. And the algorithm, I won't get into details of the algorithm, is a 12-step algorithm in which an initial solution is found using a surrogate objective function, and then the method uses multi-attribute utility functions for producing a new solution. And then they check, showing the solution to the user if this solution is satisfactory, and this process is repeated until a satisfactory solution is reached. So in this case, the results of applying this method provide not only levels of attainment of the objective function elements, but also the probabilities of reaching those levels, which is also very nice. This is an interactive method. This means that the decision maker formulates the preference function in a progressive manner. So it's a trial and error process. At the beginning, perhaps I don't have a very clear idea of what I want, but once I see the solutions the method is obtaining, I will set up my goals. Something interesting in this approach is that the decision maker ranks objectives in order of importance. That's what the multi-attribute utility function does. And this is done at the beginning of the process, and later on he uses pairwise comparisons to reconcile these preferences with the real values that are obtained by the algorithm. So this allows not only an interactive participation, but also to gain knowledge about the trade-offs of the problem, which is very useful in real-world applications, particularly when you are not very familiar with the problem. So there are some references if you want to know more about this method, which is also very old. Then the STED method is an iterative technique that is based on also on progressive articulation of preferences. Here, the idea is to converge towards the best solution in the min-max sense that we already saw, minimize the maximum deviations in no more than k steps. And this is mostly used for linear problems, starting from an ideal point, and then the algorithm has 6 steps. But one of the limitations of this technique is that it assumes that the best compromise solution does not exist if it is not found by the algorithm after performing these k steps. And if this happens, then the user has no idea what to do. You know? It basically fails, and that's it. There is no information on what could be done. So this is not very nice for the user. Another problem is that it does not explicitly capture the trade-offs between the objectives. So the weights are not reflecting this judgment value of the decision maker, are only artificial quantities. So this is also not nice, and operations research people don't like this. So there are some references on this method if you want to know more. And the last one, called SEMOPS, sequential multi-objective problem solving, it involves also interactively the decision maker. First, it uses a surrogate objective function based on the goal and aspiration levels. This has to be expressed somehow by the decision maker. And then the goal levels are conditions imposed on the decision maker by external forces. That means perhaps the customers or my boss, somebody above me, is imposing this goal, and the aspiration levels is what personally I would like. You know, this is the sort of solution I would like to have. So The aspiration levels, of course, may change during the search because this is what I want, and humans tend to change their preferences over time. But these external forces, these goals, I cannot change. This I have to live with this because this is imposed by somebody else. So it operates using a 3-step procedure that involves a setup, an iteration, and a termination process. So setup is basically structuring the problem and several auxiliary problems that you have to solve. And for this, it uses a surrogate objective function. Iteration involves cycling between an optimization and an evaluation phase until reaching a satisfactory solution. And it terminates when either a satisfactory solution is found or the decision maker concludes that none of the solutions are satisfactory, and then he gives up and says, that's it, I'm done with this problem. And if you want to know more, there are also some good references on this method. So, okay. With this, for summarizing, for finishing this first lecture, there are many others techniques available, several mathematical programming techniques available for nonlinear optimization. Kaisa is a very good reference for this, Kaisa's book, which, as I said, unfortunately is not possible, I think, to buy the book anymore, but I'm pretty sure you can get it in the internet. And some of these algorithms are very easy to implement. Others are cumbersome because they require second derivatives or they require implemented some graph theory algorithms. But in general, the book contains a very nice review. And of course, there is a proposal because this book is a spin-off of Kaisa Mietinen's PhD thesis. She proposed a method called Nimbus, which is described in the last part of the book, which is also very nice for nonlinear multi-objective optimization. But in general, these techniques have several limitations. The main one is that they tend to generate a single solution for each execution of the algorithm. Another disadvantage, another limitation is some of them require that the objectives and the constraints are differentiable, in some cases twice differentiable. Other techniques cannot be applied to disconnected or non-convex Pareto fronts. So there are several serious limitations. However, these algorithms have one important advantage. They are very efficient, computationally speaking. They are very fast, as opposed to metaheuristics. Metaheuristics are not very fast. It's only that today we have very powerful computers. So this can make their cost affordable. However, as we will see in the last lecture, there are problems in which metaheuristics are not very useful because the objective functions are very expensive. And in these cases, we cannot afford to use metaheuristics. And we will get to that to see how to deal with those problems. So these limitations motivated, of course, the use of metaheuristics. In this course, we're going to talk particularly about the so-called bio-inspired metaheuristics. Just in case you're not familiar with the definition of metaheuristic, a metaheuristic is a high-level search procedure that applies some form of rule or set of rules based on some source of knowledge. This source of knowledge, in the case of bio-inspired metaheuristics, are normally something that exists in nature. For example, natural selection, or the way in which the birds fly, guided by a leader, or the way in which ants move, looking for food. There is some rule that is guiding this search. The rule may be deterministic or may be probabilistic. In the case of evolutionary algorithms, they are stochastic because the rule is not deterministic. This rule is probabilistic. And basically, what we want is to explore the search space in a more efficient way. What do we mean by more efficient? More efficient than what? More efficient than brute force, than enumerating every possible solution. Anything that is affordable to me is okay. And for me, it may be affordable to find a solution in 1 hour, in 1 day, in 1 week, in 1 month. It depends on how patient I am for waiting for this solution. It depends on the computer resources I have. Some people can afford using a supercomputer for running a metaheuristic. Others can only afford using their laptops or desktop computers. It depends on that. Yes? There are deterministic metaheuristics and there are probabilistic metaheuristics. There are of the two types. In here, most of the ones we will see are probabilistic. We will talk about taboo search. Taboo search is not probabilistic, but all the others are completely deterministic. No, we cannot say they are not deterministic. They are probabilistic, which is bad in a sense because we cannot guarantee convergence. And mathematicians get very scary about that. They say, oh, what do you mean? But you have to consider this. We are the last line of defense in optimization. People come to us. We don't come to people. When they are desperate and they cannot solve the problem, they don't care. You know, they could use Harry Potter to solve the problem, and they will be fine with that. All they want is to find a solution. So if you tell them, I cannot guarantee this is the best solution, that's fine. That's fine. I'm not aiming for that. So they are so desperate, they don't care.
For certain problems, if given the same metaheuristic,
you will find different results. Yeah.
So why call them non-deterministic?
Well, you can call them non-deterministic. It's just the idea of non-determinism in the computer science sense is a little bit different, right? In here, they are probabilistic. I like more some people use non-deterministic, and I have no serious objection for that. It's just that the lack of guarantee has to do with the sampling, not with the nature of the algorithm. So for me, it's different. A non-deterministic algorithm is something that really is magic, right? You don't know how it produces a solution. And the non-determinism can be mapped to determinism in an exponential way. This is not the same. They cannot guarantee the solution because you are sampling the search space. The population is the sample. So this is really the lack of guarantee lies on that, not in the nature of the algorithm itself. So for me, it's not exactly the same. But if you want to call it non-determinist, I think it's okay. I won't argue on that. It's just they are different. So from the many metaheuristics that are currently available, the class that has become very popular in the last 20 years is the so-called bio-inspired metaheuristics. And they are supposed to be inspired on some biological metaphor. For example, evolutionary algorithms. The inspiration is Darwin's survival of the fittest principle, which you are well aware of. Most of these algorithms are stochastic because they use a probabilistic selection function. So we will talk about evolutionary algorithms, particle swarm, and colony optimization, differential evolution, artificial immune systems, all these we will see later on. But there are many others, as I said. I have this book called Clever Algorithms. It has some really strange, bizarre metaheuristics. Actually, people in operations research don't like this. They make many jokes about people who work with metaheuristics. Most of the bio-inspired metaheuristics we have operate on a set of solutions. This set of solutions is normally called the population. And this is the sample of the search space. So at each iteration, we use this population. And of course, a clever use of the population will allow the generation of several elements of the Pareto optimal set in a single execution. This is normally not possible in mathematical programming. So this is an advantage if we know how to manipulate this population. Now, bio-inspired metaheuristics require very little information about the domain. We don't require derivatives, second derivatives. We don't require the Pareto front to be convex, non-convex. They are very general. They are less susceptible to the shape or the continuity of the Pareto front. But they also have disadvantages. The main disadvantages are, first, they cannot guarantee convergence in most practical cases. There are proofs of convergence for very specific conditions. We can prove convergence of some multi-objective metaheuristics, but not in general. But the most serious concern is not this, because as I said, in the problems in which we use metaheuristics, nothing else can be used. This is the last resource we have. The serious constraint is the second one, that they normally have a high computational cost, much higher than mathematical programming techniques, because of their stochastic nature. So this requires some sampling. We have to evaluate many solutions to get an idea of how to guide the search. And this, of course, may be unaffordable. Back in the year 2004, I attended a DAX tool seminar, the first DAX tool seminar on multi-objective optimization. These are very famous seminars organized in Germany. They put experts in a certain field, locked in a castle, and in these castles, the rooms have no TV, nothing. You know, all you have to do is to think and talk to your colleagues, and they force you to interact with other people, even if you don't like that. It's very interesting. It was a very interesting experience because half of the people were multi-objective evolutionary optimization guys, and the other half were multi-objective mathematical programming guys. And the first time we met, we had so many misconceptions about each other. Basically, we thought all mathematical programming techniques were garbage, and they thought the same about evolutionary algorithms. That was very interesting. You know? So we both thought, you know, whatever you use is garbage, has no use in practice. And we were wrong because at the end we concluded that both algorithms were garbage. It's just this was the garbage we knew how to use, so that was good. You know, we sort of were happy at the end. But their algorithms are very, very fast, very efficient. And many of these algorithms, they can be parallelized efficiently, so you can use. But I remember at that seminar, there was a guy, a Japanese guy, he approached me and he asked me, he said, I have this problem of designing the wing of an airplane. The objective functions are so expensive that I can only afford performing 500 objective function evaluations. And these 500 evaluations will consume six months of supercomputer time. This is my budget. So he raised the question, do you have a multi-objective evolutionary algorithm that can solve this problem? And the answer was no. At that time, we didn't have any. Now we have some. But at that time, it was not possible. So there are problems like that, that is so expensive to perform a single evaluation of an objective function that you cannot use a metaheuristic because, you know, 500 evaluations here is nothing. We normally perform 20,000, 40,000. And there are crazy people, they go for 1 million evaluations, 2 million evaluations. I always joke with them and say, you are trying to use brute force, right? This is no longer a metaheuristic. You are just generating all the solutions you can just to make sure, you know, this is the best solution you found. But they are unaffordable in some cases. Now there are techniques to do this, but back in 2004, we didn't have that many tools. So, okay, we're going to move now to the second lecture, which is on evolutionary algorithms. And something really interesting happened to me in my life. I consider myself a very lucky guy, although I'm unlucky in every other sense. You know, whenever I don't like to gamble because I always lose. I don't like to buy, you know, lottery tickets because I never got anything. And if I get something, is for sure it's going to be bad. It's going to be a bad thing. But in terms of research, I was very lucky because back in '94, when I was a PhD student in the US, I didn't know what to do in terms of research topic. And a professor there who was from operations research originally, he suggested me to do multi-objective optimization. Of course, I had no idea what that meant. And I started looking papers about this, and I realized there were no papers, very few papers back in '94. And I thought, you know, this is good. Because if you find many papers on a topic, that means many smart people have already worked on that. If there are very few papers, it's because of one of two reasons. It's either too difficult, you know, many people tried and failed, or nobody knows of this topic. And I was lucky it was the second case. Nobody knew of this topic. So many things I did back in the 90s, you know, all these things were garbage. But since I was the first to do this, many people started to cite this and say, well, I can outperform the algorithm. Of course you can outperform the algorithm if it's garbage. This I already knew. But at that time I was able to publish this. Today it will be impossible to do it. So I was very lucky in that. And many people who started with me, and this is also very strange, I call it the course of multi-objective optimization. These guys ended up doing something else. I don't know why. Very few remain in this area from those who started back in the 90s. Very few people are still here. We will see in the history, because I know all these people. And others, they didn't do multi-objective. For example, Kalyan Moidev, he was doing something else. And then he got hooked into multi-objective, moved to this area, found it was very profitable, and stayed here. with us. But he was not there at the beginning. There were very few people there at the beginning. So, okay, we will start by talking about evolutionary algorithms in case you're not very familiar. I'm assuming you are, but if you're not, I will go very quickly on this. The idea of using techniques based on the emulation of the mechanism of natural selection is actually very old. It's not that recent as people would think. It can be traced back to the early 1930s, although the first algorithm is actually from the 60s. In the 60s, the three main techniques based on the notion of natural selection were developed. It was the genetic algorithm developed by John Holland in 1962, evolution strategies developed by Hans-Paul Schwefel and Ingo Reichenberg in Germany in 1965, and evolutionary programming developed by Lawrence Vogel, David Vogel's father, in 1966. John Holland died 2 years ago. Lawrence Vogel died like 10 years ago. Hans-Paul Schwefel is still alive. Ingo Reichenberg is also still alive. The German guys are still alive. Something very interesting is the motivations of these algorithms were completely different. You know, Holland wanted to do machine learning, and he thought nature was the key for machine learning. Hans-Paul Schwefel and Ingo Reichenberg, they wanted to solve an optimization problem in engineering because that was their PhD thesis topic. And this objective function turned out to be non-differentiable. So this guy, Ingo Reichenberg, he had to invent a method. And he did. It worked, but then his advisor told him, okay, you know, this looks like non-deterministic. So you cannot graduate with this algorithm unless you prove convergence of the thing. And this took him like 4 years to do. He finally managed to do it, and he could graduate. But that was the evolution strategy. And Lawrence Vogel wanted to do forecasting. You know, everybody wants to be rich, right? You want to predict the behavior of the stock market. I will be happy with being able to predict what my wife wants tomorrow. This I cannot do. I don't think any algorithm can do that. But forecasting is complicated. If you look at these algorithms that do forecasting, normally they are right 50% of the time, which is the same as tossing a coin, right? You don't need an algorithm. Just toss a coin and you will get the same percentage. So it is a very difficult task. And he tried to do this in the 60s. For you who are very young, computers in the 60s, you know, my iPhone is a supercomputer compared with those computers at that time. You know, my students now that I tell them, you know, when I was young in the 80s, computers have memories measured in kilobytes. So what do you mean? They don't know about that. They know about gigabytes, terabytes, petabytes. When you tell them, you know, just the byte, you know, 8 kilobytes. They think I'm joking. That's what they spend in one message they send with their cellular phone today. But that was the memory computers had in the 80s. You can imagine in the 60s. There was no computer power. So these things failed. Failed because the computational resources available were not enough. And these things are stochastic, so they need a lot of memory. So all these approaches were collectively denominated evolutionary algorithms, and they were used for several years for single objective optimization. Although there are some really interesting stories. For example, genetic algorithms were not conceived for optimization. This was a historical accident. They were meant to be used for learning, for classification. But David Goldberg made a mistake, and then everybody else followed. So the basic way in which an evolutionary algorithm operates is very simple. And I think I have a picture here. Yeah, it's easier with the picture. You start by designing a set of solutions. We call this the population. This set of solution is randomly generated. Normally, a uniform distribution is used. And this initial population, you evaluate each solution. You have an objective function, of course. The objective function will define what we call the fitness function. It's not exactly the same. It depends on the problem you are solving. But it's, of course, related to the objective function. Evaluate these values. Then you select the solutions that have the best objective function values, which are the fittest. You know, they have the best fitness values. And these individuals reproduce. Evolutionary algorithms are very nice because in here, this is a simulation. So everything is allowed. For example, an individual can reproduce with itself. This is not possible in life. Right? You cannot reproduce with yourself. But here is okay. You recombine with yourself. Of course, your children will be identical. There is nothing to improve there. It could be worse, but it's not going to be better anyway. So you can create new designs using this reproduction, and then these designs will eventually improve the fitness of the whole population, and you keep doing this until you decide to stop. There are some criteria for stopping, and also many variations of this. For example, selection normally in our simulation is probabilistic. That means the worst individuals in the population, those with the lowest fitness, have a probability higher than 0 of being selected. One of these guys can be very lucky and may get to be selected, and he will be reproduced. Of course, you can change this and make it deterministic. In evolution strategies, the selection is deterministic. That means low fitness, they die, for sure. In nature, it's like that. Not with us, with other species. With us, we can match with anyone as long as the other person is available, right? That we can match. There are no restrictions. But in nature, many animals, they impose restrictions. They have tournaments, they fight, and the strongest is the only one who is allowed to reproduce for the good of the species. For us, we don't care. We are so many, what the hell, we can afford having a few low fitness guys over there. It's okay. We are not going to disappear as a species. It's fine. Now we have mutation. Mutation in nature is an interesting phenomenon. Mutation is really an error when copying DNA from the parents to the offspring. We are made of an alphabet that consists only of 4 letters. These are the nucleotides. And every form of life on Earth has only these 4 letters. So when copying these DNA strings, sometimes there is a mistake. They produce proteins. It's a complicated biochemical process. But in the process, sometimes there is a mistake, and this is the mutation. Mutation is not an operator in nature that generates new species. Mutation is an operator that all it does is to produce a modification in the DNA of the species. Normally, for example, in humans, mutations, also in animals, produce strange physical characteristics. For example, this rhino, which is white. There is a rhino somewhere which is white. It's very uncommon. This is actually a mutation. The only thing that produces new species in nature, as far as we know, is geographical isolation. Because when you isolate a species, the selection pressure is different. If you are in an ecosystem in which everybody is physically strong and you are competing for resources, you have to be able to defeat these strong guys or you won't survive as an individual. However, if this same individual is moved to a different location and in this other geographical location he is the strongest, he will evolve in a different direction. So that's how nature works. Of course, mutation won't ever produce a guy who goes through walls, who can launch X-rays and all this. Like the X-Men, this cannot be produced by mutation, of course. It doesn't matter how much you mess with the DNA, this thing is not going to come out. It's only normally diseases and physical malformations what is the outcome of mutation. So the operation is very simple. I always tell my students, evolutionary algorithms are so simple that even engineers can understand them. If engineers can understand that, everybody in the world can do it. Right? You don't need to be a computer scientist. This is the sort of algorithm everybody. Well, I have known people from sociology, other areas, they even understand this thing. They don't know how to use it, but that's fine. As I said, even if you use it wrong, perhaps the result is correct. So no need to worry. Implementation is very easy. So, okay, who was the first who actually came up with the idea of using evolutionary algorithms for multi-objective optimization? This is a very interesting question. According to David Goldberg in his book, he mentions that it was this guy, Richard Rosenberg. His PhD thesis is from 1967, very old. That's the year in which I was born. This guy, he was trying to solve a problem in which he was dealing with two biochemical properties. And for whatever reason, he decided, instead of trying to solve this problem with two objectives, he decided to transform one of the objectives into a constraint. And then he solved with a genetic algorithm this constraint single objective optimization problem. In his problem, these properties, which were closeness to some specific chemical composition, were the objectives. But since he didn't actually develop a multi-objective technique, he missed his chance. He is not the pioneer. He is not the inventor of the first multi-objective evolutionary algorithm. That honor goes to this guy, John David Schaefer. John David Schaefer, he is already retired from Philips. He worked in industry all his life. In his PhD thesis from 1984, see how many years after Rosenberg, he developed the first actual implementation of a multi-objective evolutionary algorithm. This thesis is actually very interesting, and is probably the most highly cited PhD thesis in multi-objective optimization. Most people cite it, but this is like Holland's book. Holland's book, most people who do genetic algorithms have cited his book at least once in their lives. Most of the evolutionary computation people I know, they don't even have the book. And those who have the book have never read the book, because the thing is so hard to read. You know, when I have problems to sleep at night, all I have to do is to grab John Holland's book. I can open randomly in any chapter. I will fall asleep in no more than 20 minutes, guaranteed. It's incredibly boring. But, you know, that's the book. It's the first book on genetic algorithms. You must have it. So I had to buy the book. I could not resist temptation. And at some point I said, what the hell, you know, I teach genetic algorithms, I have to read this thing. But it's impossible to read. Believe me, I tried several times. I gave up after like the second chapter. Sometimes I only can read the introduction, and that's how far I can get. But, you know, I have it. I have it. One day I will probably read it. And this thesis I also have. And this is actually a very interesting thesis. I got it from Schaefer because it's very difficult to get. It's a very interesting work, although now it looks very naive. The algorithm he proposed, he called the vector-evaluated genetic algorithm. And I'm now in a new project. I'm trying to write a book on the history of EMO, of evolutionary multi-objective optimization, and I'm conducting some interviews with these guys. David Schaefer is, of course, the first. I sent him a questionnaire. Hopefully one day he will send it back. So this algorithm was published in the first international conference on genetic algorithms, 1985. You can imagine 1985. 1985, I was starting my undergraduate degree as a civil engineer. You guys weren't even born at that time. And this guy was already, you know, in his first conference on genetic algorithms. This is now called GECO. This conference is called GECO. It's a very famous top conference in evolutionary computation. At that time, David Goldberg told once, in 1985, there were about 12 people doing genetic algorithms in the world. That was the community of evolutionary computation in the world. This is the paper he published. Very interesting paper because he cites Pareto's book, but he doesn't use the concept of Pareto optimality. And this I asked David Schaefer once, and he gave me the very evasive answer. You know, he could not really tell me why he didn't use Pareto optimality. So we will see how it works, but first, let's get to the taxonomy of multi-objective evolutionary algorithm. This is Kalya Moidev's book. This is the cover for those outside India, because in India there is a very cheap edition you can get for a very low price. But those of us who are not lucky enough to buy it in India, we have to pay like $100 for this thing. That's what I paid for this book long time ago when I got it from Wiley. So we have the non-elitist, non-Pareto. All the non, it means bad, right? This is like the worst you can get, but we have to see these methods. These are the oldest. Then we have the non-elitist, Pareto-based. This is not that bad. It's getting better. As we remove the nons, it's getting better. Then we have the contemporary. This is my book. If you want to buy, this is still available. This is very old, but I still get royalties from this book. It's amazing. The contemporary approaches, so we have elites. You see there is no none in here, so this is good. But even these algorithms are already today very old. So this is what people are using today, and we will get to this in the last part. Decomposition, indicator base, and reference points, as in the NSGA tree. So we will get to that part. So we will start with the very old methods. Very old means from the 90s. So the non-elitist, non-Pareto-based method. So these are the original methods that were proposed. These algorithms are, of course, very simple, very naive. They are very fast because they don't have complicated data structures. They don't have complicated algorithmic structures. But they only work with few objectives, and they can solve very simple problems. So we will start with lexicographic ordering. As I told you before, some people read this method, about this method. They didn't know how to implement it, so they implemented this wrong, and they call it lexicographic ordering, which is fine, because evolutionary computation people didn't know what lexicographic ordering was anyway. So they say, yeah, if you want to call it like that, it's fine. Do whatever you want. So this was, we saw how this works. How was this implemented? Well, what they did was to randomly select an objective at this generation. And this seemed to work. Then somebody very clever in the mid-90s realized that if you do this with a genetic algorithm using something that we call proportional selection, which is the most common technique for selecting solutions, then this turns out to be equivalent to a linear aggregation of objectives. That means this is not going to work with non-convex Pareto forms. And actually, doing random doesn't even work with more than 3 objectives. It doesn't work very well. But, yeah, they try, other people adopted this. They compare only with respect to the most important objective, and if there is a tie, then they use the second most important, and so on. There are variations of this. It is still being used. Some people have used this without knowing this is lexicographic ordering. They call it something else. The main advantage is very simple, it's very efficient, but of course it doesn't work very well, and it cannot scale. It doesn't work properly when you have more than 2 objectives. Even with 3 may work sometimes. But some people have used this. Actually, there is another very old paper in the same proceedings in which Vega was proposed. There is this paper on compaction of circuits using symbolic encoding. Foreman uses lexicographic ordering. Some French guys use this for robot motion planning. And more recently, in 2001, this guy, El Moudani, used it for crew rostering for an airline. So it has been used. It's just, most of these people don't call it lexicographic ordering. They call it something else. Then linear aggregating functions, we already saw this one. We just add all the objectives. So we transform a vector optimization problem into a scalar optimization problem, which is what the genetic algorithm can do. The main advantage, again, is simplicity and efficiency. The main disadvantage is defining the weights, as somebody asked, is not trivial. There are actually algorithms to do this. But in the old days, we did this in a very naive way. You know, any way it occurred to you, it was fine. And regardless of the weights adopted, this approach is unable to generate non-convex portions of the Pareto fronts. And there are proofs of this. For example, this paper has a very nice geometrical proof that this is not possible. Of course, people, evolutionary computation people are among the most creative people I have met in my life. And I have met many, many creative people. Some people, they don't want to accept something that is very evident, very clear. So my good friend, Yao Shujin, he came from fuzzy logic. And one day he approached me and he said, I found a way of producing non-convex portions of the Pareto front using a linear aggregating function. And of course, my first reaction was, either this guy is crazy or he's stupid. I knew he was not stupid, so I thought, this guy gotta be crazy. And he showed me the paper, and then I told him, okay, you win, but you are cheating, because what he actually did is he transforms the problem into polar coordinates, rotates the Pareto front when it's non-convex, making it convex, and then he can generate solutions in there. But of course, he proposed a whole algorithm to do that. And I was sitting there thinking, isn't this like too much effort just to make this work? Why do you have to use a linear aggregating function? There are better ways of doing this. But of course, he was proving his point. It is possible to generate non-convex portions of the Pareto front using a linear aggregating function. It's just not in this space, right? You have to do the mapping to a different search space, and then it's possible. Of course, this thing cannot be generalized. He did it for 2 objectives, then for 3, and that's it. Then he dropped this idea. Over the years, linear aggregating functions, as I told you, became the closest thing to the devil. Back in the 90s, when I was starting my career as a researcher, I graduated in 96. If you read, for example, a paper submitted to the Transactions on Evolutionary Computation that started in 97, you put in the abstract, and for solving this problem, I use a linear aggregating function. That's it. This is a rejection. There is no need to read the rest of the paper. Because linear aggregating functions were supposed to be the wrong way of solving a problem. Why? Because you cannot produce the non-convex portions of the Pareto front. And some people say, well, what if my problem has a convex Pareto front? Then don't use evolutionary algorithms. You know? They will kick you out anyway. So this was bad. Nobody liked linear aggregating functions, and they say, forget about that, don't use them. In the 2001, 2002, in that time, beginning of the 2000s, some people show evidence that linear aggregating functions were better than what we call Pareto-based selection in combinatorial optimization. But since people who do Pareto-based, we are non-linear guys, we don't care much about combinatorial, say, yeah, why don't you take your algorithm and go there, right? Don't bring it here. We are doing non-linear here, so don't mess with us because we don't want to use linear aggregating functions. But they do work in some cases. Of course, in the old days, many people used linear aggregating functions in many problems, controllers. This was a PhD thesis, very strange topic. The design of optical filters for lamps. Guard antenna geometries, my friend David Van Belduisen. So there were many applications in the old days. Now we go with Vega, the old algorithm, the oldest ever. David Schaefer received the Pioneer Award in evolutionary computation some years ago from the Computational Intelligence Society. In his PhD thesis, he developed this algorithm which he applied to a machine learning problem. It was a classification problem. And this is a very simple, naive, and intriguing algorithm at the same time. So this is how it works. This is the population of a simple genetic algorithm. Okay, it's the same population. So he creates subpopulations as many as objectives. So let's assume I have 2 objectives. I will create subpopulation 1 and subpopulation 2. So I will divide by half the population. I have 100 individuals, so 50 will go to subpopulation 1, the other 50 to subpopulation 2. Okay? Now, in this subpopulation, in 1, I will select the best solutions with respect to objective 1. Subpopulation 2, the best with respect to objective 2, and so on. Then I will do this shuffling of the population so that the best in objective 1 recombine with the best in objective 2. The idea is recombination is some sort of interpolation, so I should produce a compromise between objective 1 and objective 2. This is the idea. Some people analyzed this algorithm in the mid-90s and they concluded, again, if you use proportional selection, this is equivalent to doing linear combination of objectives, linear aggregation. It's the devil right there. But this was the first algorithm, so it was okay. Nobody cared about this. It worked. Of course it worked. He tried with 2 objectives, and he tried with a very simple test problem, which was very famous for many years. So very, very naive. Main advantages is very easy to implement. It's, of course, very efficient. The main disadvantage, it has some funny disadvantages. One, of course, is if you use proportional selection, and David Schaefer will deny this, but this is a fact, Vega behaves as a linear aggregating function. And then the other problem is, oh, this thing again. Windows is alive, right? That's what I don't like, Windows 10. The other problem is something that David Schaefer called the middling problem. He used a funny word. But if you think about the way Vega works, it's not only that he's not using Pareto optimality, but his selection mechanism opposes Pareto optimality. Because if you are selecting the best in each objective, then a non-dominant solution is not the best in each objective unless you are in the extremes of the Pareto front, right? You want the best trade-off, not the best objective function value. So if you always select the best, it's not only you are not using Pareto optimality, you are going against Pareto optimality. This, of course, David Schaefer will deny. He says you are wrong. And he said, well, there are some strange problems sometimes, something he calls the middling problem. Well, the middling problem is that he's opposing the whole notion of Pareto optimality. But as I said, it's okay, because this was the first algorithm. So everything was possible. There is no mechanism to maintain diversity, which is something very important, as we will see later. And it was used by several people. Even I used this a long time ago. I found a very strange application, the design of combinatorial circuits. Other people use this for automatic control problems, ground gather pollution, and so forth. Epsilon constraint, we saw epsilon constraint. So some people use an evolutionary algorithm for doing the single objective optimizations of the epsilon constraint method. And of course, this is very costly, but it works. And there was actually one guy back in the year 2006, Marco Laumans, who developed an approach that was not that inefficient, but it only works for discrete search spaces based on the epsilon constraint. So it's possible to use these hybrids, but it's tricky. Now, it's relatively simple, but it requires the nadir point, which, as I said, is difficult to find in more problems with more than two objectives, and it's very expensive to use this. You can do it if you can afford it, but if not, then I don't advise you to use it. Some people have used this in engineering, for example, to design submarines for automatic control, in environmental engineering, and so on. Then we have the so-called target vector approaches. This is what I did in my PhD thesis. These are methods that today people are not using anymore. They are very rare. Basically, in here we try to minimize differences between a solution we found and a target goal, like the min-max method, for example, or goal attainment. So something very important here, these methods also use aggregating functions, but these are non-linear aggregating functions, not to be confused with linear aggregating functions. A non-linear aggregating function, if you define it properly, it's able to generate non-convex portions of the Pareto front. This many people didn't understand in the 90s. So there were hybrids, for example, with goal programming, with goal attainment, with min-max optimality. This is what I did in my PhD thesis. The main advantage in here is computational efficiency. Disadvantages, you need normally the ideal vector you need to produce, which are the goals. And also, some of these techniques have some misbehaviors under certain conditions. For example, goal attainment, there are some cases in which it doesn't work. And there's some very specific conditions. I won't get into details, but it has problems. Also, other approaches require the goals to be defined in the feasible region, which in some problems is difficult because you don't know if the target that you decide is attainable or not. But they were used a lot in the old days in structural optimization. For example, I used it in a problem in robotics a long time ago. Has been used for designing digital filters. So David Goldberg, you know, he is a very interesting character, a civil engineer who sort of became a computer scientist on his own. In 1989, he was young, he was like 36, 37 years old. He decided to write a book on genetic algorithms. And some people who met him at that time tell me that he had a box of about this size that contained all the papers and PhD theses ever published on genetic algorithms back in 1989. And he read all this and published this wonderful book, which is not that easy to read. It's not as bad as Holland's book, This is actually the book that people read to understand genetic algorithms, because we couldn't understand Joe Holland's book. And at the end, this book has some source code in Pascal, because C was not that big in the 80s. It became famous in the 90s. And in his book, he provides a very nice review of everything what was known about genetic algorithms until the mid-80s. I had the opportunity to visit David Goldberg's lab in Illinois back in 2003. And he told me that for several years, he kept collecting papers on genetic algorithms with the hope there will be a second edition of his book. When he reached the paper 10,000, he gave up. He said, there is no way I'm writing a second edition of my book. Something similar happened to me with Multiobjective. The first edition of my book was published in the year 2002. Right after we published the book, it was obsolete already, because there were so many new algorithms. So since the book was very successful, of course, this was not a Harry Potter's book. You know, very successful means you sell 200, 300 copies a year, and then publisher is happy. Because this was a very expensive book, published with Kluwer. Then they merged, and Springer was interested in a second edition. We wrote a second edition, got published in 2007. It was a tour of force. It was very difficult to write a second edition. And we were very concerned about the price of the book, because the first edition was very expensive. So I negotiated with my editor that the book will not cost more than $100. You know, publishers, they are very clever. Okay, no more than $100. So they say $99. It's less than 100, it's fine. And they say no more than 1,000 pages, and then the book will cost less than 100. So I asked, do you mean number pages or actual pages? And they didn't know, of course. This is non-deterministic for a publisher. So they went and asked. And I say, number pages, that's it. You know, the book has like 1,200 pages, but only 1,000 are numbered, because this was a constraint. It was a hard constraint from the publisher. But it almost cost me a divorce, because I had to spend so many hours writing the second edition. So sometimes they ask me, will you write a third edition? Of course not. I will never do that. I won't even try. But I have had this very bad idea. Sometimes when I cannot sleep at night, I have these bad ideas. There is the devil inside my head trying to write a second volume, which is different from a third edition. That I may do one day, but not now, not for some years. And this book, of course, will never see a second edition, because David Goldberg is now retired. He has his company, and he's devoted to education and other ideas. So in his book, he reviewed everything that had been done on genetic algorithms, including multi-objective optimization. And the only thing available on multi-objective optimization was Vega. So this is a very interesting story. In his book, he describes in about 1.5 pages how Vega works. He criticizes Vega, and then he sketches the idea of an algorithm. He says, if I had to solve a multi-objective problem with a genetic algorithm, I would do it like this. And he gives sort of an idea, not an algorithm. And this 1.5 pages originated a whole area of research. So his idea was very simple. It's called Pareto ranking. Pareto ranking means we have to select solutions based on Pareto optimality. So those solutions that are non-dominated in the population should be given a fitness value that is not really related to objective function value. It's related to Pareto optimality. So the best possible fitness, these solutions should get. And then all of them, all of the non-dominant solutions should get the same fitness value, so that when selecting, they are sampled the same, because they are equally good. All of them are equally good. Then you remove non-dominant solutions, classify again, assign another fitness value, and you keep doing this. Actually, the original NSGA is the closest to Goldberg's idea. But of course, there are very clever people. Some people figured out there were ways of doing this more efficiently. We will get to that. So this algorithm is non-dominant sorting, but as I say, he didn't propose the algorithm. He only gave sort of an informal description of the idea. And the process of classifying solutions is known as Pareto ranking. Goldberg, who is a very smart guy, he also figured out something else. He said because of stochastic noise, if you keep running the multi-objective genetic algorithm with this non-dominated sorting business, every solution will become equal. Everybody will converge to a single solution over time because random numbers in the computer are not really random, they are pseudo-random. So this introduces a stochastic noise. So we have to block the selection process to avoid this from happening. And he said, guess what? I will give you a technique that I just developed very recently that you can use to block the selection process. So he proposed to use something called fitness sharing. This second component is a part of every modern multi-objective evolutionary algorithm, and we gave it again a fancy name. It's called the density estimator. The density estimator is this mechanism that avoids that all the solutions get equal. It allows the generation of different elements of the Pareto optimal set in a single run. And of course, there are many ways of doing this. Goldberg proposed his sum algorithm, fitness sharing, which was introduced in 1987. We will get to the details in one of the practical sessions. The idea is to subdivide the population into several subpopulations based on similarity. Similarity can be measured in objective function space or in decision variable space. And it uses a parameter called sigma share to distinguish how close solutions are from each other. There is a threshold that you have to define. Yeah, here is the expression. So this parameter you have to provide, this sigma share, and basically imagine you have solutions in, I will put this in objective function space, but you can do it in any space. So I have many solutions scattered. So I take one, I take this, I draw a circle. My circles are very bad, but you're better doing this. And the radius of the circle is sigma share. So any solution, I'm going to put some solutions here. Any solutions inside the circle, this is bad, because I want the solution in the center of the circle to be alone. So what he does is he divides fitness by the number of solutions inside the circle, including myself. So this can never be 0, because at least I will be in the circle. So the ideal is that this is 1, that I'm alone in the circle. If nobody else is in the circle, fitness remains the same. As I get more solutions inside the circle, fitness decreases proportionally to the number of solutions. So it's a very interesting algorithm because it's very simple and it will spread solutions. It works like magic. It spreads solutions. It's similar to clustering. What is the problem with fitness sharing? Sigma share. How do I know the value of sigma share? And Kalya Moidev, in his master's thesis, he proposed a way of computing sigma share, but it was very complicated, so most people didn't use that approach. So we will see how multi-objective people solve this problem. The solution was not to use fitness sharing, get rid of the thing. But at the beginning, some people tried to use it. So what I call pure Pareto ranking were algorithms developed in the old days in which they didn't use the density estimator. They only used non-dominant sorting because they thought it was not necessary to have the density estimator. So there were a few applications in the old days, particularly in engineering, in which they were not interested in producing many solutions along the Pareto front, just a few. So if that's what you want, perhaps the density estimator is not that important. So there were people using this in groundwater problems, pump scheduling, mainly is engineering, planning of power distribution systems, and so on. Then we have MOGA. Carlos Fonseca, a very smart guy from Portugal, goes to England to do his PhD at the University of Sheffield with a very famous guy, Peter Fleming. Peter Fleming is an automatic control guy. At that time was already famous in his area. And he decided to start working with genetic algorithms for multi-objective optimization because he had some real-world problems on industry that were multi-objective. And Carlos Fonseca was the perfect match for him because they developed what is considered by many, including myself, the most powerful algorithm of what we call the first generation. It's the first layer of algorithms. It was called MOGA, This was, multi-objective people are very creative except for the names. We need to bring a Japanese or some guy from other place. Names, we're not good at names. So this thing, he said, well, I could not think of any name for the algorithm. So he called it multi-objective genetic algorithm, which is very confusing because many people will develop a multi-objective genetic algorithm and we didn't know if they were referring to their algorithm or to Fonseca's algorithm. But yeah, okay, thank you for the name, which is totally uninformative and useless. But that's fine. It was a very nice algorithm, and the problem he had to solve, he pioneered many areas with this problem. This problem was what we call now many objective because it had more than 3 objectives. It had uncertainties, it had incorporation of preferences, it had many, many difficulties. He was designing some gas turbines for Rolls-Royce. The thing, of course, was implemented in MATLAB because, automatic control people, that's all they know. They think C is a letter of the alphabet. They don't know it's a programming language. So they say, okay, MATLAB, they do it in MATLAB. And the code was available, but you had to pay. And this is the thing with computer scientists. One of the basic principles you learn in computer science is you're not supposed to pay for software. That's why we don't want to use Windows. We can use Linux for free. So if you can avoid paying for something, you will do it because it goes against your own principles. Because we are supposed to know how to write programs, so why should we pay for somebody else's programs? Right? We can write our own. Of course, I could not write an operating system, but I don't want to use one for which I have to pay. So he released the code, but you have to pay for it, so not many people were willing to pay for the code. But the algorithm is very interesting. He improved the original Goldberg's algorithm for non-dominated sorting. This is how MOGA works. He uses this rank. So he takes the first solution and compares this solution against everybody else in terms of Pareto optimality. And this value, this P, means how many solutions dominated this solution. So of course, if this solution is non-dominated, P is 0. Nobody dominated me. Then fitness is given by 1 divided by rank. So any non-dominant solution will get a fitness of 1. Dominant solutions will get a fitness value that decreases proportionally with respect to the number of solutions that dominate. So it's very nice, right? Very nice fitness function, very easy to do. Also, he uses fitness sharing, but Fonseca was a very smart guy, so he proposed a way of computing sigma share, which was very easy. He considered that he wanted as many circles as solutions he had in the population, and for computing sigma share, he only took the extreme values of the objectives that were known at that time, and divided that by the number of solutions, and he could get a very easy geometrical expression to compute sigma share. So it was a very sort of trivial expression, but he avoided the user the trouble of having to define sigma share. So this was a very nice algorithm. Of course, was not that efficient, was order n squared, but it was very effective in the comparison studies that people performed in the mid-90s. We found that this was the best algorithm. This was better than NSGA, which was proposed later. And it was also better in terms of results than MPGA. That was another algorithm that was developed at that time. It was implemented in MATLAB, which motivated its use in automatic control. Many people in that area use it. And the implementation, however, was complicated. If you read the original paper, the implementation is cumbersome. The first time I taught my course on multi-objective optimization, I asked my students to implement it. It's really messy. And Fonseca is quite a character. He's a very nice guy, very smart guy, but he's a complicated guy. So there was this time in which I was teaching a course in Spain, of course in Spanish, but you know the Portuguese, they always understand Spanish. So this is very, very dangerous for us because we don't understand any Portuguese. You know, native speakers of Spanish, it's impossible for me to understand Portuguese, but they do understand every word I said in Spanish. So I was teaching this course, Fonseca was seated at the back, and when I talk about his algorithm, I said it was non-elitist. if you read every paper on multi-objective evolutionary algorithms, they all consider the algorithm to be non-elitist. I read his paper, implemented the algorithm based on his paper, and he never mentions he uses elitism. And then after the class, he comes to me, approaches me, and tells me that his algorithm was elitist. And I say, how come it's elitist? You don't say that in the paper. Then he hesitated a bit when he realized I had implemented the thing out of the paper. I said, well, it was very obvious to do it elitist. Yeah, well, apparently not so obvious because you didn't say that in the paper. And actually, I know a woman, it was this lady, Else Duchesne, in the late 90s. Else Duchesne did a research stay with Fonseca in Portugal and developed the elitist MOGA. So I say, how come if the original MOGA was elitist, this woman who was working with Fonseca called her algorithm the elitist MOGA? This is very bizarre, right? So I don't believe the original MOGA was elitist. But Carlos will tell otherwise. He will say, he will deny everything pretty much. So this algorithm was very popular. Many people use this algorithm. This is Else Duchesne. And of course, including Fonseca himself, who developed several applications in the 90s. Then we have Kalya Moidev, of course, from IIT Kanpur. He developed the non-dominated sorting genetic algorithm. And this is also a very interesting story. This algorithm is the one that follows more closely Goldberg's idea of how to do non-dominated sorting. There is one problem, however. Non-dominated sorting, as described by Goldberg, is more inefficient than MOGA from Fonseca. And this, of course, creates a problem. So how does it work? Let me see if I have the description. Yeah. First, you have the population. You identify solutions that are non-dominating the population, remove them. These solutions are the first layer. And they get a dummy fitness value. Any value will do. For example, 1 million. All of them will get the same fitness value. Okay? So with the remainder of the population, you classify again, identify non-dominant solutions. This is the second layer. Second layer gets another dummy fitness value lower than the fitness value of the first layer. So let's say 500,000. And you keep doing this until the whole population has a fitness value. So it's not very hard to figure out that this is applying Fonseca's algorithm n times. So Fonseca's algorithm is n squared, this is n to the third. You cannot get more inefficient than that. It's hard to get that. Now, this algorithm was not very good. However, it was the first multi-objective evolutionary algorithm to be published in a specialized journal, Evolutionary Computation, which was created by Goldberg's group. In evolutionary computation, there are two main communities, Vogel's friends and Goldberg's friends. And normally, who is a friend in one group is not a friend in the other. There are a few exceptions, like myself. I'm a good friend of the two groups. But it's a very interesting story. I won't get into the details. So they fought over one evolutionary operator. One of them claims mutation is all you need. The others claim crossover is the most powerful. And this is like a religion. You know, it's an act of faith. And whoever is in each group, they hate the other group. It's quite interesting. So in this paper, which is also very interesting, Deb mentions MOGA, but he doesn't compare results with respect to MOGA. He compares with respect to Vega. Vega, you know, everybody could defeat because it was a very naive algorithm. Everybody who compared NSGA against MOGA in the mid-90s, including myself, systematically, MOGA was able to outperform NSGA, which is probably the reason why he's not comparing the paper. But that's okay because he managed to get the paper accepted, right? And MOGA was published in a conference, and then there was another paper in the Transaction on Cybernetics. So this is on order n to the third because the non-dominant sorting is less efficient. However, this algorithm, something interesting is easier to parallelize this algorithm than Fonseca's algorithm. So it was used. It was not as popular as MOGA, but it was used. Another interesting story I can tell you, back in the 90s when I was a student, I wrote to all these guys. I sent emails to all these guys asking for their code. So Fonseca sent me a voucher to pay for the code. He said that If it was for academic purpose, it was only 50 pounds. I'm not going to pay 50 pounds for this. Kalya Moideb, he replied to me and said, yeah, I will send you the code in a few days. That was 24 years ago. I'm still waiting for the code. He has it now in his website, but he never sent me the code. He promised he will do it. That's nice, right? You don't say no. It's just you don't send it. But that's okay. That's fine. I have students like that the code was so dirty, they didn't want people to see it. And say, well, I am your advisor, right? I'm like your father. If I can see this thing, you can show it to the world. If it's embarrassing, both of us will be embarrassed. And I have released code that is embarrassing. Actually, it's scary. You will hear some stories. But, if you want people to use it, you have to release it. And that's one of the key aspects of NSGA 2. Since the very beginning, the source code was available. Was not the case of the original NSGA. But this I understand, because sometimes you rely on students. So you ask the code to the student, and again, they say, I will clean it up. This cleaning up may take 20 years, or longer than that, depending on the student. But it was used by some people. Was never as popular. The original NSGA was never as popular as MOGA. I think we have to stop now. It's 1. Yeah. All right. Now, what we're going to do now is we're going to try to execute by hand the two algorithms we saw in the morning for non-dominated sorting, because this is a very basic algorithm we need to use. Actually, ideally, you should try to implement this in a computer, but before you try to do that, and you can, of course, do that if you want, I think you should make sure you understand how the algorithm works. So I designed a very simple example. This is an example in which we have 10 solutions. They are just numbered in the first column. And these are 3 objectives, objective 1, 2, and 3. So please copy these values, and then I will ask some volunteer. I hope there is a volunteer that comes at the front to execute by hand the first algorithm, which is the naive algorithm. This is actually very, very easy. Second algorithm is a bit tricky, but the first algorithm is very easy. All you have to do is to compare solutions. Remember, we are minimizing objectives. So for a solution to dominate another solution has to be less equal in every objective and strictly less in at least one. If these conditions are not fulfilled, it does not dominate the other solution. Okay? Just keep this in mind before executing the algorithm. So please copy, because I cannot show at the same time the problem and the algorithm. So once you have the data, we will move to the algorithm, and I will ask somebody to come at front and start executing the algorithm by hand, so that you can see how it works and how it's comparing solutions. Why is the algorithm simple but at the same time inefficient? And what will be the final outcome of the algorithm, which is which of these solutions are non-dominated. That's what the algorithm produces. Algorithm number 1. Then we will do number 2, which is a little bit more complicated. It does exactly the same. It's just it does it in a different way. It will seem perhaps a bit complicated to do it by hand, but in the computer it's more efficient than the first algorithm. Okay, be careful. I hope you can see the numbers well, that you can distinguish them well, because I use this weird font in Windows, and some of these numbers don't look very nice. After we complete the exercises, I will show you a website where you can download an implementation of this in C, of an algorithm that is better than algorithm number 2. It's similar to number 2, but it's a bit better. In case you don't want to implement it, but of course you are welcome to implement these algorithms in any programming language you want. We did it in C, and in my course in Mexico, I asked my students to implement a much more sophisticated algorithm. But they are in computer science, so they are supposed to know those things. So they have to implement things. And the assignments are also quite difficult. They have to do a lot of reading. But that's okay. It's a PhD course, so they are supposed to know what they're doing. That's not always the case, but this is the assumption. Okay, please let me know when you are ready so that I can change to the next slide. Are you okay? Okay. So this is algorithm number 1. So I need a volunteer. Volunteer, or should I choose a volunteer? You look like a good volunteer. Yeah, this guy looks like he wants to do it. Okay. So we can use the board here. Can start in there. So bring your solutions, please. Don't forget your solutions because we need them to execute the algorithm. So algorithm number 1 is very, very easy. First step is we set a counter, I, which starts in 1. So I is equals to 1. This is step 1 of the algorithm. And we are going to create an empty set of non-dominant solutions, P prime. P prime at the beginning has no solution, so you can put the curly brackets and it's empty inside. Of course, P prime will contain the solution at the end, right? Okay, so it says for a solution J that belongs to P is the population. This is the 10 solutions we had. Where P is the population, please pay attention to this. J is different from I, so if I is 1, it cannot be 1. Any other value is okay, except for 1. Check if the solution dominates, if J dominates I. If it does, then you go to step 4. Okay? Obviously, if this is not the case, you just move to step 3. And if there are more solutions left in P, increase J by 1 and return to step 2. Very, very simple. Okay, so let's do this step first. So you are in, let me return. Oh, wrong computer. Let me return. So in I equals 1, you are in the first solution. So we go to the second. And it says check if solution J now is 2, because J cannot be 1, so J is 2, and we compare if this solution dominates solution 1, because that's what the algorithm says, right? You are going to check if J dominates I. So can you tell me if solution 2 dominates solution 1? To dominate, it has to be less equal in every objective and strictly less in at least 1. So you can see 5 is greater than 3. So it does not dominate. Okay? So what does it say? If it dominates, goes to step 4. That's not the case. So we go to step 3. So are there more solutions? Yes, we have more solutions left. So now J was 2, we will increase J to 3, right? So we started J equals to 2, and now we move to 3. And we go back to step 2. So now we are going to compare, and this guy is going to continue, but we now have to compare solution 3 with respect always to solution 1, okay? So again, the question, does solution 3 dominate solution 1? Yes or no? No. Then we increase J. So we move to solution 4. So does solution 4 dominate solution 1? No. Okay, keep going. Yes? No, because 3 is greater than 2, right? So keep moving and tell me if any of the other solutions until you reach 10, if any of them dominate solution 1. None of them. Okay. If there are no solutions left, because in here it says, check if there are more solutions in P. If there are no solutions left, otherwise, you add I to the set. That means solution 1 is non-dominated because nobody else dominates the solution. Okay, so we have the first solution that is non-dominated. Very easy, right? Now, we increase I by 1. So now I is 2. And we check if I is less equal than n. N is 10 because we have 10 solutions. We still have to go. And we go back to step 2. So again, we're going to choose j such that j is different from I. But pay attention. In here, I can use 1 because 1 is different from 2. I cannot use 2. Every other number I can use. So I will use 1, 3, 4, 5, 6, 7, up to 10. Okay? So first checking I need to do is, does solution 1 dominate solution 2? No. Then you have to keep going. So keep going and tell me if solution 2 is non-dominated or if it is. If somebody dominates solution 2, then you will stop. So is anybody who dominates solution 2? Solution 8, if you see, 3, 1, and 5. So it's equal or less. So solution 8 dominates solution 2. Therefore, solution 2 cannot be non-dominated because it's dominated by someone. So if it dominates I, then go to step 4, and you have to increase I by 1. So 2 doesn't get into the list because it's dominated. So now we move to solution 3. And we have to compare 1, 2, 4, 5, 6, everybody except for 3 against this one. So can you check solution 3 with respect to the others and tell me if it is non-dominated or it's dominated? So what about solution 3? Is it dominated or not? Non-dominated, okay. Then add it to the set. We now have one more non-dominated solution, and we move to solution 4. So is it clear how the algorithm works? Of course, it's very inefficient because we are checking several times the same solutions with respect to each other. But that's okay. This is, when you are a student and they ask you to do these things, this is sort of the naive approach to do it. So we move to solution 4, and again, we have to compare 1, 2, 3, 5, 6, 7, 8, 10 with respect to 4. So can you compare and tell me, is it dominated or non-dominated? Solution 4. Is anybody dominating solution 4? It's non-dominant, so we add it to the set. So we have now 1, 3, and 4. So this is where you see that it's not reflexive, right? Because you measure this in one direction, and then you measure in the other direction. Sometimes it's non-dominated in the two directions. So, okay, now we move to solution 5. So we have to compare everybody else with respect to solution 5. Is it dominated or non-dominated? Solution 5. 9. Solution 9 dominates solution 5? No. No, because this is 1 and this is 4, right? No, but we are comparing with respect to 5. We are in 5 now. Don't get ahead of yourself. Yeah, we are in 5. Let's do one by one. So is 5 dominated or non-dominated? It's non-dominated. You have done everything, right? That's what you're saying. Okay, so 5 is non-dominated. We move to 6. Is 6 dominated or non-dominated? It's non-dominant, okay. So we move to 7. What about 7? 7 is dominated. Who dominates 7? 6 dominates 7. So you see, you have to be careful. You have to do it. A computer will do everything, but you are sometimes a bit lazy. You don't want to compare everybody, but you have to do it. 7 cannot be in the set because it's dominant. What about solution 8? It's non-dominant, so we add it to the set. We only have 2 more solutions, 9 and 10. So can you tell me for 9, is it dominated by someone? 1 dominates 9, so it's dominated. What about 10? Are you sure? 6 dominates. So those are the only non-dominant solutions. 1, 3, 4, 5, 6, 8, using the naive algorithm. So are there any questions on how this algorithm works? It's very simple, right? Implementation is also very simple. It's tedious because you have to compare in every case one solution with respect to everybody else. So imagine you had 10,000 solutions, 10 objectives. You know, in the assignment I give to my students, they have to generate 3,000 random solutions in 5 dimensions. So it takes some time. It takes some time.
Definition of dominating system.
Excuse me?
Definition of dominating. When is one solution said to be dominating the other?
If the other one is, if it's less equal and strictly less equal in every objective and strictly less in at least one. So, for example, in here we say 6 with 9. So you see 6, 0, 1 is never worse and is better in at least one. 0 is better than 1 because we are minimizing.
That means again, one or more solution can dominate the other. Because here 1 and 2 both are dominated by one time.
Sure, sure. This can happen. But we are only comparing by pairs. This is important. When you do the comparison, it's one at a time. One solution at a time. Yeah, because otherwise you could do weird things. So is it clear how this algorithm works? It's very easy, right? So, and the outcome of the algorithm is this list containing the solutions that are non-dominated. So if I had to plot the Pareto front, what I will do is to take the decision variable values of those solutions and plot them. These are already objective function values, so I can directly plot these objective function values because this is the way this works. So it's very, very, thanks a lot. Yeah, it's very easy. So let's find another volunteer for algorithm number 2. Yes?
Consider I have already compared, when it is 9th solution, that case already I have compared 9 with other cases. Only 9th and 10th comparison is enough, not why I will again 9 with 1, 9 with 2, 9
Oh, because you have to compare with everybody else, always. For
first time 1 with 9 is done, 2 with 9 is done, 3 with
yeah, but you are comparing in the opposite direction. Remember, it's not reflexive. So if I compare 1 with 9, it's not the same as 1 with 9. It has to be done in the 2 directions because Pareto dominance is not reflexive. I may be better if I compare in this direction, but when I do it in the other, I'm not better because sometimes they are incomparable. It doesn't dominate, but the other one doesn't dominate either. So that's the problem. That's why it's so tedious. So the obvious question is, can we do this in a better way, right? More efficient, because it is clear here we are performing several comparisons. It's very inefficient, so can we do it better? Sure, we can do it better. So this is the second algorithm. It's a little bit more complicated because in here, you're going to be placing solutions that later on will be removed. So at the beginning, it will assume most solutions are non-dominated. And then it will be removing solutions. But by doing this, you are going to gain time when you implement this in a computer. You will see this algorithm is more efficient. So we need a second volunteer. Now, here you are going to be cheating because you already know the answer. But the thing is, the set will have a different contents, at least at the beginning. So do we have any volunteer for algorithm number 2? You seem like a good volunteer. You're a mathematician, right? So you should be good for this. Do you have these solutions? Okay. Because this one is a bit more complicated. So in this case, if you see, the algorithm doesn't start with the empty set. It says, now let's assume P prime is the same set, contains the first solution. So first assumption is, let's assume for a moment that the first solution is non-dominant. We know in this case it is, but before executing the algorithm, the first algorithm, we didn't know this. So we will start with P prime equals 1, is the index of the first solution. Don't worry about this. Of course, if the first solution is dominated, we will remove the solution from the set. So don't worry about that. And we set a counter I equals to 2. Okay? So I is equals to 2. So now we set J equals to 1. And take a look at what the algorithm says. We are going to compare solutions I and J from P prime. If I dominates J, then you delete the J member of P prime. Okay, deleting. This is trickier. So let me see if I can get back here. So it says to compare who against who? 2 to 1. And if 2 dominates 1, then you remove 1, right? Because you lose if you get dominated by someone, right? And assuming you are non-dominated, but if I find somebody who dominates you, you are out of the set. You lost my trust because somebody was able to dominate you. So we compare solution 2 with respect to solution 1. This we can say because we already did it. We know this guy is non-dominant, right? Nobody is going to dominate him. And it says, okay, this doesn't happen. Then it says, if J is less than the cardinality of P prime, the cardinality is 10, so then increase J by 1 and go to step 3. So that means J now goes to the second solution, and we return compare solutions I and J. So we are going to be doing this until we go to the last step, because whenever this is not true anymore, we have to assume the solution is non-dominated. Nobody was able to dominate it. Here is a little bit messy. I think one of my students who messed with this algorithm introduced on a step. Yeah, well, this else that is weird. That if the J member of P prime dominates I, then you increase I by 1 and go to step 2. But in here, we are measuring in one direction first. In this direction, we already know we are going to keep iterating, increasing J. And in this particular case, nobody will be able to dominate I.
So, but here I am. No, we will not increase J because J is equal to cardinality of P dash. It is not less than P dash. But initially J was 1 and cardinality.
Oh yeah, cardinality is 1. You are true. You are right. Yeah, you are right. So we don't increase. We go to step 5. Insert I in P prime, and if I is less than n, n is 10. Yeah, cardinality of P prime at this point is 1. Then we increase I by 1 and go to step 2. Yeah, you're right on this.
So every solution can dominate itself.
What?
Every solution can dominate itself.
Well, we are not really comparing somebody against itself. If you see in these algorithms, we always skip this step. We avoid dominating yourself or being non-dominated. No, yeah. We are avoiding this because it will make no sense. You don't compare with yourself because dominance is defined with respect to everybody else, not with yourself. Yeah, you won't dominate yourself, but yeah, you don't want to. It's not necessary to do that. So, okay. So we continue, and we were here, right? Increase I by 1 and go back to step 2, in which J is set to 1 again. The step that, if I remember well, my student added, because you have Kalyamoy Dev's book, and this algorithm is called continuous update in the book, he doesn't include this step. What happens if the J member of P prime and I are mutually non-dominated? This is sort of assumed in the algorithm. That is a trivial case, but some people get confused with this.
I guess this is correct, sir. That is nested if condition.
Yeah, that's normally the. If you implement this in C, it will work, even without putting this condition. But
for the
Exactly. But some people get confused, so we had to try to explain this in a more explicit way as a special case, the mutual non-dominance. But yeah, so can you continue to execute the algorithm? So what will happen is she is going to be adding solutions, and each solution that is added, then you have to compare the others with respect to what is already in this set. But of course, at the moment that somebody dominates that solution, you have to remove the solution from the set. And then you just move to the next solution. You don't keep comparing. You stop at that point and leave the loop. So in that sense, it seems to be similar to the other one, but it's more efficient, although this is also order n squared, it's more efficient in the sense that these check-ins require about half of the comparisons of the previous algorithm. But the execution by hand, at least some people find it to be more complicated in this algorithm than the other one. Of course, the outcome has to be exactly the same. If you don't produce the same output, you did something wrong. But it should produce the exact same outcome. So solutions, if you remember from the previous exercise, for example, I think solution 2 was dominated, right, by someone. So solution 2 at some point has to be removed from this set. Because I think there was somebody who dominated that solution. Yeah, solution 8. What was, no, 9? Yeah, do you have the solutions? These are the solutions. Yeah. Yeah, you have the solutions, right? So no, 2 is non-dominated. This is 2, 3, 4, 5. Yeah, 7 is the one that is dominated. These two algorithms are in the slides. I just copied the pseudocodes to this other presentation, but you already have in the slides from the morning. It's just in the morning I didn't stop to explain the algorithms.
You are supposed to initialize J with 1, go to step 2. Increase I by 1 and go to step 2. J is equal to 1.
If you increase I, you have to go back to step 2. Yeah, because 2 is dominated, right? So at some point, it will come out that 2 is dominated by somebody. I think 9 dominates 2. But she hasn't reached solution 9. So something strange about this algorithm is when you execute it by hand, you feel that you are doing more work than in the previous algorithm. But in the computer, it's a lot faster to do this one than to do the previous one. So algorithm 1 is for humans. This is for computers. Let's get a picture of my students. Yeah, I think the eraser is there. So who is in P prime right now?
I have P prime now 1 to 4.
1, 2, 4. But 2 is dominated. So 2 should not be, yeah, 2 should not be in that set.
Sir, actually 8 dominates 2. 8 dominates 2. It will take time. Just carry on.
Okay, keep going, but at some point you have to remove that one. Yeah. I got lost on the execution, but not dominated. So it should be. You missed that. 2 is dominated, but 3 is not dominated. Please try to execute it because you need to get the flavor of this algorithm, which, as I said, is less intuitive than the previous one. At the end, it should produce the exact same result. It's not as easy to interpret as the first. So what will happen with this algorithm, at the beginning, you will have most of the solutions inside the set, but it will be removing solutions. And at the end, it will contain the exact same solution. Unless, of course, you make a mistake. You make a mistake, you are going to miss some non-domination.
You also need to add G. You need to add GS.
GS is a number of dimensions.
GS you also need to add.
Otherwise, go to 5.
J is less than 2.
No, J is 3, no? So it is 3. So it is not strictly less than. So otherwise, go to step 5 and
actually you missed 3. It should be there in 3 dash. 3 is non-dominating.
So where I missed 3?
Let's start with 3. Let me check. Just add it to the center. Just add it. Yes. Now J is less than magnitude of 3 s.
Yes.
And then go back. But at the same time, after you compare in one direction, if I dominates J, you compare if J dominates R. You do it the opposite way. And this is the trickiest step in this algorithm. Because by doing that is that you are saving evolution.
But according to the previous solution, like 2 should not be there. Should be 1, 3, 5.
2 should not be there. I think there was a mistake in the execution. But don't worry, this is understandable. Yeah, I think we should restart the execution because there are some solutions. I think 6 also should not be there. There are some solutions. Yeah. We got messy at some point. No, 6 is there. It's 1, 3, 4, 5, 6, 8. So let's start. more slowly. So we will start again. P prime equals first solution, count I equals to 2, J equals to 1. Okay? So we are going to compare, it says compare solutions I and J from P prime. So if I dominates J, then we need the J member of P prime. So who is going to be compared? Is the solution I is 2, is the solution 2 with respect to solution J from P prime. J is 1 from P prime, so it's the first solution in this set, solution 1. So we know I does not dominate solution J, right? So we check, and this was the original mistake that this guy pointed out. If J is less than the cardinality of P prime only has one solution at this point. So the cardinality is 1 and J is 1. So 1 is not less than 1. We will have to increase J by 1 and go to step 3. But in here, that is not the case. So what we have to check is the other direction. If the J member of P prime dominates I, then increase I by 1 and go to step 2. So we have to do that step. So we check now if solution 1 dominates solution, the first solution dominates solution I, which is solution 2. If 1 dominates 2. So is that the case? Solution 1 dominates solution 2? No. So if that happens, we will have to increase I by 1. But if not, then is this weird step. If the two are mutually non-dominated, then we increase J by 1. If this holds that J is less than the cardinality of P prime, which is 1. Otherwise, we go to step 5. So we eventually go down. I think the way we were executing before the algorithm, we were sort of skipping checking of dominance in the other direction.
2 will be deleted when I will be 8.
Exactly. It's just, we were doing more steps. We were executing more steps than necessary. So the first part should be like that. And now we go to J equals, this is still J1, because this doesn't hold. We insert I in P prime. I will be solution 2. And then if I is less than n, we increase I by 1 and go back to step 2, in which J will be again B1. Oh, she's very fast. She's already solution 3. Yeah, so we're going to keep adding solutions. It will be 2, 3, 4, 5, 6. After adding solution 6, then we will start deleting solutions. At the beginning, the algorithm will keep adding solutions. Don't worry, some of the solutions, of course, are dominated, but at some point, they will be removed from it. So if you execute the algorithm properly, you will be adding 1, 2, 3, 4, 5, and 6. After 6, then you will start removing solutions. One, two, three, 4, yeah.
Actually, you need to increase J.
Yeah, J should be in 4 now. And then you have to increase I. I goes to 6. I is 4, So don't blame me for the code, because it's not my my pseudocode. It's from Kalyan. think so far we are doing okay. 1, 2, 3, 4. Then I should be 6 and J should be 5.
Increment I. Again increment J directly. Because it does not dominate.
Has anyone been able to execute the algorithm successfully? Or you have everybody as non-dominated in your execution? I6. So far, so good. Now we are getting there. I think most people are not following, but that's okay. That's okay. This is a tricky algorithm. The first one is a lot easier, right? Yeah, you can imagine Kuhn's algorithm. Kuhn's algorithm is extremely difficult to do by hand. Up to 6. And 7, then you will get to delete 2. Before.
Then 2 will be deleted.
Yeah, no, at this point you will delete. After the 6. You will see. You will see that after that step, you will get to delete.
No. When I will be 8, I will.
I equals to 7, I guess it will continue, no? 3, 4,
Yeah,
5,
yes.
6.
Actually, 8, no one, 7 dominates no one.
No, 7 dominates no
No
one.
one.
So I'm not writing every step.
You can skip it.
Exactly, yeah, that's okay. That's okay.
Add 7 to the set.
We will add 1, 2, 3. So
Add
J
7
will,
to the set.
when J will be 6.
But I think 6. Yeah, 6 dominates 7. 6 dominates 7. So, yeah.
And J is 6.
Okay.
Sir, I dominate J, na sir?
I do not dominate J. Now, J is not strictly less than P dash because it is 6. So now P dash will become 1, 2, 3, 4, 5, 6, 7.
That is where you will start removing solutions because
Now I dominate J.
I when I dominate J, then J has
you delete that solution.
Yes.
Delete it.
No, 2. J will be deleted.
Yeah.
J is deleted. 1 and 3. J is deleted. After that, J is less than J is less than P dash. So then J is equal to J plus 1. J is 3, I is 8.
My execution, I never got 7 into this. But you managed to get 7 inside this set.
Okay. Did I have I done something wrong?
I'm not sure.
No, you are
But, yeah, I think pretty much. So far it's
correct.
J is less than P, so J is 4, I equals to 8, 8 and 4, 8, no, 8 and 4,
because in my execution,
Sir, actually,
7 never gets
this
into
is nested, this if and else is nested within this if and else. If I does not dominate J, then we need to know this step.
That's what I did when we started.
Every time
we
we are
started the second time. But I think she kept doing this from the original execution. That's exactly why we restarted, because I realized
actually this if and else is nested within
nested with the other step.
that. If I does not dominate J, then we need to come here.
after deleting,
No.
okay.
If
You have to check dominance in the other direction.
No, then what is this? Otherwise, what is step 5?
this is nested within this key.
Yeah, within this.
Let me write. Because 7 will not be deleted now.
Exactly, because 7 should have never been.
6 dominates 7 actually. 6 dominates 7.
That's what I was saying, that in the execution 7 will never get to 7. 2 is okay because it will be deleted later on, but 7 should never get it. I know it's very confusing because the else is not clearly, and I have to move a few things around so that it will fit in one slide.
The else is with the first thing.
Exactly, it's with the first thing. So the reason why this is more efficient is because you have to, which is what I was trying to explain in the second execution, that you have to check in the 2 directions, dominance, each time. So you check first in one direction, and then you check in the second direction. The remember, P prime dominates I. It's in the same step. I think this guy already got it. So first, yeah, you do only 1, j equals 1, that's all you do. And you get 1 and 2.
And then else.
Exactly. It's a very messy code. But as I said, it's not my code. So in the first step, you start with 1. Then you have to compare. It should be I equals 2. So you compare the second solution with the first solution. Then the second with the first. So you have to go to this edge. Second with the first. And check dominance in the 2 directions. It will happen that they are mutually non-dominant. So you add the second solution to the set. You now have 1 and 2. And then increase I by 1 and go back to step 2. So now I will be 3. And when I is 3, you have to start again with j equals 1. You go j1. So you compare solution 3 with P1 prime, so the first element of P prime. Then you compare in the opposite direction, this first element with the third solution. Then you go to j equals 2, you increase j by 1, and compare again A3 with the second element of P prime, and in the opposite direction. It will happen they are mutually non-dominated, so it's this case, and then you add 3 to the set. So now you have 1, 2, and 3. Then you continue, I is now 4, and you start J1 again, and check. A4 is compared with respect to the first solution in P prime, and you check the 2 directions. Then J2, you do the same, A4 with respect to the second solution. And then j equals 3, you check in the two directions. Again, it will happen that they are mutually non-dominated, so you add solution 4. So at this point, you have 1, 2, 3, and 4 in the set. Then I is equals 5. When you reach 5, again, j is equals 1, because you go back to step 2, and check again solution 5 with respect to the first element of P prime. Then the opposite direction, 1 with respect to 5. You increase j to 2, 3, 4. Reaching 4, again, is the case that solutions are mutually non-dominated, so you add solution 5. So far you have 1, 2, 3, 4, and 5 in the set. So far it's the same. It's the same that she did before. Now I is equals to 6. You check again, so it's solution 6 with respect to the first solution in P prime. Check in the 2 directions. J is 1, 2, 3, 4, 5. And then it turns out they are mutually non-dominated, is this step. and you add solution 6. So you have 1, 2, 3, 4, 5, 6. So far, so good. Everybody has been added, okay? Then I is 7. When I is 7, you start again, j equals 1. So you compare solution 7 with the first element of p prime. You do it in the two directions. J is 1, 2, 3, 4, 5, 6. And then once you reach 7, it turns out that the solution is dominated. So you have to remove the jth element of p prime because dominates solution A7. So the 7th solution. And that's why solution 7 never gets into the set. It never enters the set. So after that, I is equals to 8. J again is equals to 1 because we go back. And then we do J, we check solution 8 with respect to 1, solution 1 with respect to 8. Then we go to the second solution, solution 2, when J is 2, 8 with respect to 2. And it turns out solution A dominates solution 2. And that's it for solution 2. You have to remove solution 2 from the set. So now we have 1, 3, 4, 5, 6. And then J is equals to 3. I remains the same, it's still 8. And we continue checking 3, 4, 5, 6. And after 6, we find solutions are mutually non-dominated, so 8 gets added to the set. So 7 was never in the set, 2 was already removed. So at this point we have 1, 3, 4, 5, 6, 8. These are the solutions we have. Now I is equals to 9 and j is equal to 1. But at this point, solution 9 doesn't dominate the first solution in P prime. But the first solution in P prime dominates solution 9. So solution 9 doesn't get into the set. So we move to I equals to 10 is the last solution. J is equals to 1. We check 1. We don't do 2. We do 3, 4, 5, 6. And in the 6, it turns out that the fifth element of P prime dominates solution 10. So solution 10 cannot be part of the set. And the final outcome of the algorithm is 1, 3, 4, 5, 6, 8. Same as in the previous one. So the confusion was here with the else. The else is very confusing. Because the else is true, it belongs to the first if. So it's part of, it should all be like a single line over there. The second one. Mm-hmm.
One in the if else, then again in else, if else.
Exactly, yeah. It's a little bit tricky. So this algorithm, as I said, is less intuitive than the other algorithm. If you manage to implement it correctly, this is faster than the other algorithm.
Worst case time complexity.
It's also n squared, but in this case, you perform half of the comparisons as in the other case. Because each time, if you see, you are comparing dominance in the two directions. Whereas in the other case, you always do it in one direction, and then you do everything in the other direction, all the time. In this case, since you are doing both, you are saving comparisons. Because once you check in one of the two directions, this guy is dominated, that's it. You get rid of the solution. Doesn't get into the set. So it's more difficult to implement, more difficult to execute by hand, but it's more efficient. So let me see if I have, yeah. So this is another example with 4 objectives. Do you think you can apply at least the first algorithm to this one and tell me which of these solutions are non-dominated? The second algorithm was a bit messy, but I think the first you managed to do quite well. So if you copy the solutions, and I will put you the algorithm so you can tell me. There are again 10 solutions, but in this case it has 4 objectives. The other example had only 3. So one rule in multi-objective optimization, and we will talk about this later on, in something we call many objective optimization, which are problems having more than 3 objectives. As you increase the number of objectives, it will happen that most solutions will become non-dominated. It's much more difficult to get solutions that are dominated unless we increase a lot the population size. But if it's the same number of solutions, it's more likely that everybody will be non-dominated. So you can execute any of the 2 algorithms you want. I will put you number 1 because I think with that there was less trouble. But if you insist in doing the second, you can. Yeah, I will go back. I just, if you copy or you got a photograph of the set, I can go back and show you the algorithm. And as I said, these 2 algorithms are already in the lecture from the morning. It's just I took the algorithms, the pseudocode, to illustrate how they work. So that's it? You're ready? Okay. This is the first algorithm. The first is very easy, because it's just comparing one solution against everybody else. So can we have internet connection? That's some weird thing. That's from the morning, yeah. What's the this one? Yeah. If somebody finishes, please let me know which are the solutions, or you can just come to the front and write down what the solutions are that are non-dominated from these 10 solutions. No, you finished? Can you write the solution that are non-dominant?
Sir, two dominate set. Two dominate set.
Two what?
Two dominate set. Solutions.
No, I just want the outcome of the algorithm. The outcome is who are non-dominant.
Okay.
Most solutions are non-dominant. There are very few which are dominant. No, 7 is dominant. Check carefully. 1, 2, 3, 4, 5, 6, 9. Is 8
and 10.
This is the other. I'm looking at the wrong set. Okay. Yeah, there are 2 zeros. You're right. I was looking at the other one. Yeah, you're right. It's 7. So it's 1, 2, 3, 4, 5. 7 and 9. Yeah. 8 is dominated and 10 is dominated. So there were only 2 solutions that are dominant. It's 8 and 10. So you see, it's not that difficult to do this. It's just some algorithms are complicated. So let me show you we do have an implementation. Oh, wow. Okay. Oh no, I got to the wrong one. Yeah. In here, hidden somewhere. Yeah, this one. No DOM. This code is an implementation of an algorithm for finding non-dominant solutions. This was done by some students of mine several years ago. And there are 2 implementations. The first is a version of the second algorithm we saw. And the second is a variation of Kuhn's algorithm, which is much more efficient. And we also have, I think for some reason the resolution is very low, but we have an example also to test the 2 algorithms. So this is a website I designed for my book. And it contains some appendices that I could not include in the book because they require too many extra pages. And we also had some public domain software here, but this is kind of old. The new one is in the repository, which we will get to see later on. The repository has also migrated. It used to be in here, but now is in here. It's a new website, and it looks like this. And we do have several implementations here. But in the EMO repository, we don't have just the non-dominated sorting part. What we have is complete algorithms that were available in the internet at some point. And this software is free to use. You can download the code. is available in several programming languages. For example, number 7 is NSGA2 in Java. We do have also some implementations in MATLAB and in Python. We do have quite a few in here. Of course, these implementations were contributed by some people. This is not code that we wrote. Our own code is somewhere else. But there are some really interesting platforms in here. For example, there are some people from Spain who develop JMetal. JMetal is a library in Java that contains several implementations of very famous multi-objective evolutionary algorithms. PISA is a very old platform. It was developed by people from ETH Zurich, basically Stefan Bleuler, working with Marco Laumans, Lothar Thiele, and Eckhard Sitzler. There is also, this is JMetal. There is a version of JMetal that was released like 2 years ago, which is called JMetal CPP, is the one underneath it. This version, this one, contains code in C++. And it has several algorithms implemented, such as NSGA2, SPA2, the Pareto archive, MOPSOS. This is a scatter search, a cellular multi-objective algorithm, and so forth. And the new version, the CPP, contains more recent algorithms like SMS-IMOA. This algorithm is based on hypervolume. SMPSO, this is an algorithm we developed several years ago, in 2009. There is a new version of MOIA-D called MOIA-D-DE that is based on differential evolution. And there are many, many other implementations available. Some of these algorithms are not commonly used. For example, Epsilon MOIA is not very common anymore. It was used some years ago. And we will see this concept of Pareto, of epsilon dominance. There is also Sangamitra from ISI in Kolkata. She developed a multi-objective version of simulated annealing, a MOSA, and the code is available. And there are others. This one also was developed by an Indian guy. The archive-based microgenetic algorithm. These are versions in MATLAB. Yeah, MATLAB has the problem that when they release a new version of MATLAB, it normally happens, this is like Windows. They release a new version and the code that you developed for the previous version doesn't work in the new version. It's very strange, you know. How can
The moment like you are working on any programming, the next version is not able to.
Yeah, this is like Microsoft, right? To make software incompatible with yourself. It's very interesting. But there is a platform somewhere here that was developed in Singapore several years ago. And this platform became completely useless when they released number 4. Number 4 was a platform, a whole software package that was available. It was a commercial software, but the whole thing was developed in MATLAB. So when they released a new version of MATLAB, none of these things work in the new version. And nobody wanted to spend time to update it. So yeah, sometimes this happens. More recently, some people have developed implementations of NSGA3, and this is a very interesting story. We will get to NSGA3, but unlike NSGA2, the source code of NSGA3 is not available in the public domain. The reason is very funny. That, you know, Kalyan was many years at IIT Kanpur, moved to the US, and in the US he felt some pressure to get money from industry. And so a Swedish company approached him and offered him some money for a project for which he had to develop NSGA3. And he sold them the project together with the code. So because of this, he could not release and will never be able to release the code in the public domain. Now, he claims it's very easy to implement NSGA3 based on the paper. But at the same time, he says, he admits, he removed some details of the algorithm in the paper to make it not so obvious to implement. Well, it turns out it's not that obvious because there are at least 2 versions of NSGA 3. According to Kalyan, both of them are wrong, which is okay because there are already 20 variants of each of these 2 versions. But apparently none of these versions are okay. It's just people use those versions and they assume this is the correct version of NSGA 3. We will never know because we don't have the code. So that's the problem. You can sell everything, but don't sell your code. Because if you sell your code, then you cannot expect people to use your code, right? The descriptions of algorithms that is provided in papers, in computer science, we know this story very well. You always claim it's very easy to implement it based on the pseudocode that I put in the paper. All the details are there. This is never, ever true. Even the author will not be able to reproduce the thing if he just read the paper. Why? Because normally most algorithms contain these small details, what I call Coelho's constant. There is this obscure parameter in the algorithm that is set to a very strange value, 0.7525, whatever. If you remove this, the algorithm doesn't work anymore. Why? I don't know. Even the author doesn't know why. But he's ashamed to put that in the paper. So he claims, just run the thing and will work. No, that's not true. In most cases, it's not true. So it's very important. There is a whole movement now in evolutionary computation to push people to release the code. Because sometimes there are many small details that are missing in the paper. Sometimes this is not done on purpose. It's just you don't have enough room to put these details. So it's very important to release the code, unless you don't expect people to use your code. If you want to be famous developing algorithms, the code has to be available. And it's not very easy to release the code. Of course, it may be the case that your code is a bit embarrassing. That's okay, When you release code, you can put a disclaimer saying, if your computer crashes when running this code, it's not my fault. You cannot sue me and all this. And then you are perfectly fine. Whoever wants to use the code, they know the risk. So they will go and take the code. And if it doesn't work, just don't reply those messages. We developed the MOPSO many years ago. It was a very famous algorithm. And even today, it was published in 2004. Even today, people write to me asking me the code. And the code is available. It's in here. And then 1 week later, he asked me these very specific details. In line 273, there is this problem in the code. I said, well, you didn't read the disclaimer, right? I don't care if there is a problem in the code, right? You accepted to download the code, and this is how that far I will get. I won't get any farther than this. It's your problem if the thing doesn't work. I never said it will work. You asked me the code, this is the code. Does it work? I don't know. How could I know that? I didn't write the code. It was somebody else who wrote this, my student. And students normally are not reliable. They seem to be reliable, but most of the cases they are not. So my student is already a professor, so I'm not going to ask this guy, why don't you come and fix the code? He's not going to fix the code. He didn't do it when he was my student. He's not going to do it now, right? So all I do, sometimes, depending on the mood I am in, I give the email of the other guy. Why don't you go and bother the other guy? Don't bother me. You asked me the code, I gave you the code. So go and bother the other guy. He wrote the code, not me. But that's all you have to do. But it's important you release the code, because when this is hot, when people are using this, they will want to have the code. Not because they don't know how to implement it, but to make a direct comparison with your own algorithm. If you don't have the code, the author can always argue that your implementation is not correct, right? They can always say that because you were able to outperform the algorithm. We have had all kinds of stories with this. Like a year ago, we were writing a paper. We wrote a paper, we submitted to a journal, and it was almost accepted, but a guy asked to compare with respect to some obscure algorithm. After more than 20 years in this business, you already know when some reviewer asks you to compare with an obscure algorithm, that means this guy developed that algorithm. Otherwise, nobody will ever ask you to do that because nobody else knows the algorithm. Only this guy knows the algorithm. And say, yeah, okay, we can do it. So we asked the code. The guy offered the code. It was in Python. You know, you cannot get worse than that, but that's okay. You don't know how to program, it's fine. Give me the code, we will run it. And, you know, we beat the crap out of this algorithm. You know, we wiped the floor with the algorithm. So we put that in the paper, and the guy went mad. He said, no, you didn't use these parameters properly. Well, you know, your algorithm is garbage. You asked me to compare with respect to your algorithm. That's exactly what I did. You know, what did you expect me to find? You know, that your algorithm was so good? It's not good. You are the only person who thinks it's good. And then he recommended to reject the paper. I said, fine, you know, I can find another journal. But still, your algorithm is garbage. And nothing is going to change that. And nobody will ever use that algorithm. Because that's the problem in this business. In this business, you know, when you have been so long, I know many people like Kei-Shen Tan, the editor-in-chief of the Transactions on Evolutionary Computation. He's my friend. And what I have told them is in the last few years, we have this strange movement in the area, in multi-objective optimization, that we submit a paper, and then some guy, some associate editor, tells me things like, your paper is not novel enough. What does that mean? What do you mean novel enough? You know, this cannot be measured, right? How do you know? So I was telling this guy, you know, I don't like to get into these fights with editors and associate editors. Many of them are my friends. But last year when I was in Hong Kong talking to some people from there, Kei-Shen Tan works in Hong Kong now, I was telling you this, you know, with all due respect to whoever made this comment, I had been in this area for the last 24 years. So some of these associate editors were in diapers when I was already doing multi-objective evolutionary algorithms. So do you really think these guys are qualified to tell me what is novel and what is not novel? Tell me something else. You know, your algorithm is garbage, your results are not good, or you didn't run statistical measures. Tell me something that I can measure. But don't tell me it's not novel. Because I think I know more about novel than you guys. Because I have been here, I'm a dinosaur in this area. You know? I was here when the meteorite crashed the Earth. And I have survived somehow. I'm still here. So I saw all these algorithms when they were born. And I met these guys when they were very young, when they were students. And they are now big professors. But I met them when they were young. So don't come and tell me that this is not novel enough. This is what we normally tell you. You know, this is like dominance. It works in one direction, not all the time in the other direction. Just because they tell you that, don't tell me that. Tell me something else. Because if you tell me it's not novel, I will get very angry, very upset. Because I don't think these people are qualified to tell me that it's not novel. Very few people in the world could tell me this is not novel. And I'm pretty sure none of these guys is the reviewer of this paper. So they are doing weird things. So it's bad in the sense that now you get to see a lot of work by analogy, but no new ideas. And this is sad, and at the same time is very, very bad for the field. This I have criticized. I normally travel a lot, so I have been in many places, and everywhere I have told them this, because this is very bad. You know, I have very good friends that collaborate with me from other parts of the world. For example, these guys from China. The slide went away. But many of these people, for example, these guys, they develop small variations of existing algorithms in which they modify crossover, they introduce some small mechanism. And the paper is full of tables. They use many test problems, many performance indicators, lots of statistics. And at the end of the day, what they show is this, you know, Frankenstein, all this mixture of things, is marginally better than this other sort of a standard algorithm. And they get this published in the Transactions on Evolutionary Computation. They are happy because they use 20 test problems, they use 5 performance indicators, and lots of statistics. But then the question I ask them is, where are the ideas? This is not a novel idea. You know, it's probably because I'm a dinosaur, but in my time, it was more important to have a new idea. You know, the statistics, all that is okay, but that is just to back up your idea. And in here, what is the idea? You know, this is small modification. I met John Holland in '99. He was already 70 or 70-something at that time. But he was still a very smart guy. And in his talk, he said that something that he thought was very sad about genetic algorithms was that most of the work he was seeing at that time, because he abandoned genetic algorithms many, many years ago, but in '99 he attended Gecko, the first Gecko ever, and he said, well, I see many papers, I don't see ideas. And he was absolutely right. All these papers were small variations of existing things. And it's true, science is developed by small steps. But there is always some guy who gives the biggest step, and then the others follow. So the difference between a lead scientist and everybody else is that this leading scientist is able to give the biggest step. However, in EMO, it's becoming increasingly difficult because nobody wants to see new ideas. All they want to see is tables, statistics, plots of Pareto fronts, but no ideas. And that's what gets published in the transactions. And this is very bad, and I have criticized this a lot. Not because I am the one who is generating these new ideas, because I'm not. But there are people who have really interesting and nice ideas, very profound ideas, and they have a very difficult time to publish these ideas in top journals. Because we created a monster. You know, 20 years ago, we were criticized because you will write a paper on a new algorithm, and there were no standard test problems, there were no standard performance indicators. So it was pretty much the feeling. You provided some plots and say, look how approximation A looks better than approximation B. So this was like one of these art appreciation classes. Take a look at painting number 1 and painting number 2. And you have to believe me that A is better than B. So are you sure? Yeah, of course I'm not sure, but it looks kind of better, right? So that's what we did 20 years ago. And we were severely criticized, and of course, this was okay to criticize this methodology. Then in 20 years, we developed a methodology, many test problems, many performance indicators, statistical analysis, all that, okay, perfectly fine. But what about the ideas for developing algorithms? You know, I have been developing algorithms for 24 years. So it's not easy at this point to conceive new ideas. Some years ago, for example, some people will make comments, some reviewers, and this is where you notice that the student is reviewing a paper. They say things like, why are you developing algorithms if the NSGA2 is so awesome? So, again, you know, this kid, you know, you weren't even born when I was already doing this. So why are you asking me this? It's not like the NSGA2 is the end of the world, right? That's it. It solves the design of algorithms forever. Nobody will ever need another multi-objective evolutionary. Since the early days of NSGA2, we identified weaknesses of the algorithm, and we will get to that tomorrow. So we knew it had weaknesses, but it was very good in low dimensionality with few objectives. It was a very powerful algorithm. The source code got released in the public domain, so that helped a lot to make this a very popular algorithm. Fine. But is this the end of research in the area? Of course not. Eventually, people came out with other ideas, and they proposed different algorithms. Perhaps some of these algorithms are very elaborate, very sophisticated, too fancy, but they are there. And some of these algorithms are very, very powerful, much more powerful than NSGA2. So, and this will continue. But, of course, changing the paradigm is normally very difficult. Because if you, and this is very strange to me as a scientist, that we always criticize dogma, you know, like in religion. I'm Catholic, and in Catholicism, there are people, there are Christians who are fundamentalists. They don't want their religion to be questioned. And that's fine, I'm okay with that. But I am not a dogmatic. As a scientist, I have to question everything, even my religion. Some people don't want to do that, and it's fine with religion. But as a scientist, that you behave that way is very strange to me. So you have a foundation of your scientific knowledge, and you don't want anybody to question this foundation. That doesn't sound very scientific, right? Science was born from questioning nature, from questioning basic foundations of what we believe was correct 100 years ago. And many of these things we know now are not correct. So if we are fundamentalists in science, then we are not really scientists. We are not questioning the foundations. So real change comes from questioning the foundations of science. And this is something that is happening in this field. It's very strange, but it's, you know, we conceive a beast. The beast went out of control and just got crazy. And we cannot do much to control the beast. It's very difficult. Also, another problem we have is people who have been in this area for many years. They, apparently some people, particularly young people, seem to expect a lot from us. They want that every paper we produce is, you know, a breakthrough in the field, something that will completely change the field. Well, if that was the case, I will have no papers, right? It's very difficult to produce in every single paper a revolutionary idea. And we also have many mouths to feed, right? We have PhD students and they have to graduate. Even if they don't do a breakthrough, you know, they have some decent contribution. It's not a major step. It's nothing revolutionary. It's very difficult to do that today. But, you know, they have to graduate and get a job, go to the real world or whatever. So these papers are okay. I believe many of them are above average, but of course they are not something impressive or revolutionary. But still, I think they are much better than many papers I have seen in journals like the Transactions on Evolutionary Computation. So, but this is getting a very strange problem. And we don't really know why, the reasons why this happened. I have an idea of why it happened, and I will get to that through the course, but it's an interesting problem. For me, it doesn't bother me. You know, I'm too old to worry about these things. I don't need to publish any more papers. I'm okay. I can die right now, and it's fine with me. But for young people, it can be hostile, a little bit hostile. And also, there is a dangerous bias that people get to believe that that's the correct way of doing research. And that's not the correct way. You know, to produce many papers with no meaning is like producing no papers at all. People become famous for doing 2, perhaps 3 major contributions in their lifetime, if they are good scientists. And the rest, you know, is debris. It's just there, you know, these old papers. Sometimes you get lucky. You know, as I say, I have been very lucky in that sense. That some people found papers that I wrote many years ago that at that time and today I consider completely useless, but they think otherwise. They think these are great ideas. So I read the paper again. I don't see any great idea in there, but that's okay. They believe that. It's fine with me. I'm happy with this. And they are happy to cite this paper, which is the good thing. In my institution at Simvestab, there is this story about a mathematician who, it's a very funny story. This guy, he has a paper with many citations, but he hates this paper. And I asked once, why is that the guy, if he has so many, because mathematicians don't get cited that much. So why is that he hates this paper so much? He said, well, he gets cited a lot because the proof in the paper is wrong. And many people are happy citing the paper to show that the proof is wrong. And saying, you know, how is possible this guy was able to publish this? So yeah, well, that's pretty bad, right? That your most highly cited paper is a paper in which you did something wrong. But yeah, that happens sometimes. I know people, Vega, for example, was cited a lot because it was a very bad algorithm. So anybody could defeat Vega. And in the old days, everybody compared results with respect to Vega because it was so easy to defeat Vega. And it was a lot of fun, and you say, okay, I can design any sort of very naive algorithm, and still I will be able to outperform Vega. So that's nice, right? Because he got many citations for writing a completely useless algorithm. But the thing is, to be fair, is that there were more than 10 years before the first actual multi-objective evolutionary algorithm was published comparing with respect to Vega. So in 10 years, of course, this algorithm was completely obsolete already. But there was no research in between. So that's really why this happened. So in here you will find some algorithms. Some of these algorithms are very famous. Others nobody uses, and we will talk about that also tomorrow. I call them the algorithms that the world forgot. There are many of them. Some of them have crazy names. Others are really very unusual algorithms. But a few are quite interesting. But for some reason, they never became famous. This thing of becoming famous is a complicated thing. I call it, the Chinese call it the yin-yang, right? They say for the good to exist, the bad had to exist as well. So I always tell my students that I believe one of the reasons why I eventually became kind of famous was because there were many other people with very interesting ideas who, for whatever reason, karma or call it whatever you want, they could not be famous. So for me to exist, they have to exist. I know at least one of these guys. I make a lot of jokes about this guy. He is very good, very capable. He's a great scientist. He's a good friend of mine. But he is not, and he will never be famous. He says the reason is that he is not handsome, which is true. But I don't believe that is the reason. Yeah, it's true he's not handsome. He's exactly the opposite of handsome. But I don't think that's the reason. You don't have to be handsome to be famous. It's something, you have it or you don't have it. It's not possible to know, of course, what the secret is. But some people become famous, others don't become famous. So some people develop algorithms that nobody uses. Some other people develop in their whole life a single algorithm that everybody uses. So it's probably because it's a great algorithm, but it's probably also because the guy is very lucky. And he developed the algorithm in a particular moment in time when this kind of algorithm was needed, and he became famous because of this. So this is something we cannot control. But this is just some sort of reflection on this. So you will find many algorithms here, and the code is in the other web page I put before for non-DOM. This we had to develop when we wrote the book, because as I told you before, I had this commitment with Springer, because the problem I had here was my editor was somebody who worked at Kluwer. And Kluwer, they didn't know how to manage books. Goldberg will make this joke that say, they merge, but these guys are stupid. So they kept the worst name because he liked more the name Kluwer than Springer, but they kept the editorial habits of Kluwer. So this was horrible, this sort of merge of the two companies. But my editor was from Kluwer, so she always told me no to everything I asked her. She was like my wife. She always tells me no to whatever I ask her. But since I knew how to deal with this, say, yeah, this I can negotiate. I know how to negotiate with my wife, so I will do the same with my editor. So I managed to get several things with her. But as I said, she put constraints, but scientists are like this. You find constraints and then you start, and I'm Mexican, you try to find a way around constraints. Say, how can I sort of bend this constraint, make it more flexible? And one of the constraints was the book has to be designed as a textbook, because we will put it in this series that is meant to be a textbook. So they asked me, can you develop exercises, additional test problems? The book has some exercises at the end of each chapter, but we were supposed to have complementary material in a website. So we developed the website, which had, of course, no material at the time we released the book. But we promised, yeah, the material will be there. It's still not there. Like 11 years later, it's still not there. But yeah, probably one day I will do it. It's just I haven't had the time. I have the material, but it's in Spanish. It's not in English, and I'm too lazy to translate this. But the appendices are there. These appendices were in the first edition. Well, some of them. And we add them in here just to save pages, because all these, for example, I have Pareto fronts that were generated by enumeration here, and these will consume a lot of information. This, I had a friend with many computers in Spain who generated this. This is actually not continuous. We generated one solution at a time. It's just we have so many, it looks like continuous. But these are very old test problems. They are not used anymore. This is one of Fonseca's problems. There was a very funny joke about his test problem. Fonseca published a very famous survey, the first survey on evolution and multi-objective optimization in 1995. In 94, I was a PhD student, so I contacted him, and he was nice enough to send me a draft of the paper. So I read this paper in 94, 1 year before it got published in Evolutionary Computation. And in this survey, he included what he claimed to be the first scalable test program, which is true. It was the first scalable test program. However, it was scalable in a very funny way, because as you increase, it was scalable in decision variable space, not objective function space, but as you increase the number of decision variables, the problem became easier to solve. So this was really ridiculous. Scalable normally means you increase dimensionality and the problem gets harder to solve, not easier to solve. So you can imagine the jokes from the Germans, the German, oh, what kind of garbage is this? And it's very difficult to make a German laugh. This is very challenging. So if they laugh, this is very bad. So they helped me, this guy from Spain, these guys helped me with this Pareto front. We use this tool for producing graphs. And all this we put, but if you look at the website, it's not only the plot. These files, .dat, contain the solutions. So you can compare directly your approximation with respect to this, which is the true Pareto optimal front, obtained with a brute force approach using a cluster of computers. So at that time, in 2007, this was very useful. Today it's totally useless because the test problems we use are different. The field has changed. But we spend a lot of time in doing this. And some of these Pareto fronts, which we will see in the course, were very costly to generate at that time. These are the DTL set test problems, which are still being used today. But today people are having fun with other things. I have also a short tutorial. I used to have a tutorial on 2 hours on evolutionary multi-objective optimization. From time to time, I still teach this. And also, I had some other links that in the past, the idea was we will have lots of implementations here from my course, but this never really happened. Like, we have implemented some density estimators. We will get to that tomorrow. Like fitness sharing, clustering. There are some new methods based on parallel coordinates, S-energy. There are several algorithms. So all these my students have implemented. And some of these I plan to release some years ago in the public domain, but I never got to that stage. And also some algorithms that we developed, those algorithms are available in the EMO repository. But some of those algorithms are not very good. The implementation is not very good. Actually, I will tell you a story tomorrow of one of those algorithms that one of my students implemented, one of the best students I ever had. He was a very good programmer, very skilled programmer, and he could implement very sophisticated algorithms in a very short period of time. But, all these brilliant students, they always have something, Nature is like that, right? Cannot give you perfect balance. Something is wrong with these guys. So this guy, he had 2 main problems. One, lack of discipline, total lack of discipline. He hated authority, and you probably have known people like this. But that was okay because somehow he respected me, and that was okay. He didn't respect anybody else, which was not okay, but he respected me. So he got into a lot of trouble for that. But the second problem he had, this was a serious problem. This guy was obsessive, and he will do really odd things that will drive normal people will get crazy with him. So just to give you an idea, for example, we are talking of the year 2003. He has a laptop, and he came to see me claiming that the DVD reader has a problem. And I said, what sort of a problem do you mean? Like, you try to watch a movie and the movie is not displayed correctly? I said, no. When I read data from the disk, every 27 frames, a piece of information is missing. How the hell do you know that? So he explained, like, in 1 hour how the hell he knew that. And he called Dell to complain. And of course, they thought this guy is crazy, you know. Who the hell is going to check this? You know, that every 27 frames, one frame was missing, apparently. That's what he said. He was right, but it was very difficult to test this. So they sent an engineer, and he convinced the engineer. They replaced the DVD reader. I think the guy didn't believe him, but he was giving so much trouble. They said, yeah, let's replace the thing and forget about this guy. So they replaced the thing, and then next thing I know, his laptop got stolen. So I said, you know, you put so much effort in getting the new DVD, and then they stole it. So he was one of these guys. All the time he had problems. He always was complaining about his bad luck. All kinds of weird accidents happened to him. So the problem I had with him, he developed great algorithms. But most of these algorithms, I could never get the source code. Because, you know, the laptop crashed, got stolen, got burned, all kinds of stories, really weird stories. I only knew a guy that was worse than him, but this guy was a professor. This guy was really something. He was, I saw a movie in the 90s, I think it was called Pure Luck. Well, this guy was real. This guy, I knew him. He applied for US visa. In Mexico, we normally get the visa for 10 years. And he was in a rush to get his visa, so he calls the embassy asking, you know, where is my visa? Because you said you will send it to me in 1 week, and it has been 3 weeks, and I haven't received. And this is the answer the US embassy tells him. Well, you know, your visa was issued on time. We sent it through DHL. He lived in the north of Mexico. But the DHL truck crashed. It burned completely, and your passport with the visa on it is gone. What's the probability that something like this happens to anyone? You know, it's unbelievable. I could not believe the thing. When he told me the story, I thought he was joking. No, but the thing is, these things happen to this guy like every other week. It was unbelievable. But this guy is real. He exists. He's just unbelievable. So I told my student, you see, this guy, he has worse luck than you. You should not complain because you will evolve into this guy. You know, this guy was really something. So, yeah, my student was like that. So some of the code he developed we don't have. And the one he released in the public domain, at least one that is very famous, we will see tomorrow, is a disaster. The implementation is a mess. So for some years, I didn't care. You know, I said, well, you know, this is the first actual implementation I get from the hands of this guy. You know, this code didn't disappear, didn't vanish. He didn't format the hard drive by accident, didn't burn his computer, didn't get stolen. So I was very happy. But I thought, you know, it has problems. I knew this because other students tried to use the code. And sometimes it crashes in a funny way because it will produce these messages in Spanish with very bad words. It crashed in a funny way. And I told him, why did you put this? Oh, yeah, well, it's a glitch in the code. But yeah, every other time they run the algorithm, the thing will happen. And I thought, well, I should probably put a disclaimer in case somebody gets to use this. But then I thought, who the hell is going to use this code? You always think this. Nobody's going to use it. You are wrong. You are wrong. So one day, imagine this. This algorithm was developed in 2001. 2005, I was applying for a promotion in my institution. I started looking information about citations and all this, and I find this PhD thesis from Stanford. I start reading the thesis, and they say they use the algorithm this guy developed to design business, these supersonic jets used for businesses. I almost had a heart attack. I said, you know, if they use his code, they're going to sue me to hell because this doesn't work. But I was lucky enough, they didn't use his code. They re-implemented the whole thing in Fortran, which is good because, you know, if they use the code, I will be dead by now. I will be in jail probably. So these things happen. You don't know. You think nobody is going to use my code. You are wrong. The Chinese are always looking at what we do. Don't trust them. They are always sneaking under every single stone. What is this guy doing? You know, I put a paper in my website. Well, the title of the paper, next day a Chinese guy is asking me the paper. Say, why don't you wait until the thing gets published? You know, why do you need the paper right now? So because I'm going to copy your idea. Yeah, that I already know, right? At least you are telling me you're going to copy. This is a very honest guy, you know. He's telling me exactly what he's going to do. So yeah, it's fine. You know, you're going to publish a variation and then publish this in the transaction. Yeah? So why don't you just wait until the thing gets published? Give me some more time to try to do the same myself. So it's unbelievable, but that's the way this field has developed. It's not good, but that's the way it is. And the other interesting thing is we have so many people we lost in the way for very weird reasons. It's also very interesting. I don't know why. You know, Eckhard Sitzler, great researcher. Do you know what he's doing now? He said his dream was to teach, but whenever he said he wanted to teach, we were thinking, you know, well, he wants to teach at ETH, which is where he studied, the MIT from Europe. No, he wanted to teach at kindergarten level. This guy, you know, how the hell do you get a PhD in electrical engineering, computer science? This field become famous, and then the course arrives and end up doing something else. Somehow the course didn't touch me. It's okay. I'm happy as I am now. But many people abandoned the field. Other people had just bad luck because they are great scientists, but for different reasons, they didn't become that famous as other people. So it's also very strange. I really don't know why. In some cases, it's clear why. It was because they stopped publishing for a long time, or they didn't have enough students, you know, based on different conditions. But in other cases, they simply abandoned the field. They decided to work on something else. For example, Marco Laumans, good friend of mine, brilliant guy. He got his PhD also from ETH Zurich. And he liked it a lot, the mathematical side of multi-objective optimization. So he tried to get into operations research, but operations research people didn't like him. And he ended up working in IBM in Zurich. And he abandoned research in multi-objective optimization. So this has happened. Even Lothar Thiele, who was the advisor of Eckhard Sitzler, he is a very famous guy in computer architecture, but he pretty much abandoned multi-objective optimization several years ago. He still does some small projects, but there was one time in which his group was #1 in the world. So it's very, very unbelievable. And the new guys, I don't know most of the new guys. I have no idea who they are. I know a few, of course, the most famous people, we know each other, but there are many other guys now in the field, a lot of young blood. Not that many people with new ideas. It's just many people doing EMO, which is okay. You know, it's fine because we need those people too, so that the area keeps alive. You know, there is this interesting story in 2001, and this, of course, Kalyan Moidev is going to say this is not true, but it's true. This story is true. It's 2001, and he is visiting ETH Zurich. He's doing a sabbatical or something in ETH Zurich with Eckhard Sitzler, Lothar Thiele. They have the golden years of ETH in multi-object. You know, ETH is very famous university in Switzerland because they rejected Albert Einstein. So that's why he became so famous. You know? They were so tough. They kicked out Albert Einstein. He had to get back to study. Next year he applied. He got accepted. And they made lots of jokes about ETH, because it's supposed to be very difficult to get accepted there. And right across the street from ETH is the University of Zurich, which has the entrance period right after the notification from ETH. All the guys who get rejected from ETH, they go to University of Zurich. So they organized in 2001 the first specialized conference on evolutionary multi-objective optimization. They invited me to give a tutorial. So I was in Zurich for the first time in my life, 2001, you know, long time ago, 17 years ago, I was a lot younger. So I went to visit these guys at ETH. Kalyan was there. He had just published his book in 2001. I published my book in 2002. And we went for a coffee. So we were drinking this coffee. You know, I was feeling okay, very, very well. I was happy in Zurich. I really wanted to see this place, ETH, because it was very famous, and I knew there was very famous computer scientists in there. And out of nowhere, Kalyan asked me this question. He says, well, you know, evolutionary multi-objective optimization is now a very hot topic. But for how long do you think that emo is going to be a hot topic? And I was thinking, what the hell is this guy asking me? So I was trying to digest his question, and then he answered his question. And he said, I believe this is going to last about 10 years. And after that, it will be gone. So I told him, look, I really hope that emo lasts more than 10 years. And I'm going to tell you why. Because I'm going to do research on emo until I die. And I certainly plan to live more than 10 years. So I really hope this thing lasts for, I don't know, 50 years would be a good estimate. 40 may be okay, you know, I can retire and do puzzles and all this when I get old. But 10 years is, you know, has been 17 years since he told me that. But this is true. Even he didn't have much faith in the field. Most people didn't have faith in the field in 2001. They thought this was just a bubble. You know, it will explode, and people will realize one day, why am I doing emo? Let's go back to and do something more interesting. But that didn't happen. It's just people are not doing interesting things. But at least they are doing emo, which is good. It's okay. We just need to get them to do interesting things. But I know some of you will do interesting stuff. So tomorrow we will get to the algorithms, which is the part I like the most from this area. And also we will do a little bit more in the practical session in the afternoon. I will talk a little bit about the famous algorithms to give more details on how they work. Are there any questions at this point? Did you understand at least algorithm 1 for getting non-dominant solutions? Yeah, that you can execute right? Number 2 is tricky, but you can get the code. And perhaps it's easier to follow the code. The what? Ah, yeah. Ah, you got it? Yeah, it should be there. It's probably not readable.
You want this side, right? This one.
This is the one. It's tilde and then emo book. It's just the link. It's shown in very small font. Yeah, some people ask me, can I download the book from there? Of course not. Not the book. For that, you need to go to some Russian website. You can download the book, but not from there.